Um, we have sort of touched upon the different phases of matter in the last semester. And we got some background information that's going to help, because we have talked about polarity of molecules. Right? We know how to determine the Lewis dot structure and the shape. You might have to do some review. And it's bearing upon the polarity of molecule, because when molecules interact with one another in these different phases, we need to know something about their polarity and the potential for attracting one another. Okay, so this discussion, let me refresh your memory. Different types of compounds. Right, what's a compound? A compound has two or more different elements. In the formula. Right? So this one is not a compound. Right? That's a diatomic element. All right. So a compound would be maybe that. It's got two elements in it bound together in some form or fashion. Okay. So the binding that holds the molecule together, or holds the compound together, is an intramolecular bond. Intra meaning inside the molecule. Now, there's also a distinction to be made here. What's a molecule? A molecule is these different elements bound together, and they behave as a single unit. We can subdivide physically, we can subdivide water down to a single unit, the water molecule. As opposed to, this is a molecular compound. An ionic compound, on the other hand, is not composed of individual actors, individual players like the water molecule. It's an array, and I'm using an example here. It's an array of ions. This is the simplest whole number ratio. If you spill salt on a table, I've mentioned this before, and look at it with a magnifying glass, what do you see? See tiny little cubes, right? That's an indication of how these ions are arranged about each other. So what they're actually arranged as, you've got a chlorine here, and a chlorine here, and a chlorine here, one behind and one in front, right? So each sodium has 6 chlorines around it. And then each chlorine has sodiums around it too. Right? So it's an array bounded by the shape of the cube of these sodium chloride ions. So if we were to write the formula for that cube, it would be, I don't know, I'm just guessing, 10 to the 23rd. Right? 10 to the 23rd. It would be a huge number of ions, but they'd be equal in number. So we reduce that to the simplest whole number, and that's why we write the compound sodium chloride is 1 sodium and 1 chlorine, when we know that in ionic compounds, that's not reality. That's just easier to manage, 1 sodium and 1 chlorine. As opposed, this is an ionic compound. So what we often refer to this as the formula unit, rather than the molecular formula. The molecular formula, and let's go back to our types of bonding, right? Ionic, and there's also covalent, right? Covalent bonding is what kind? Think of the electrons. What are happening with the electrons? With an ionic compound, the electrons have been transferred completely from one to the other. So now you have a positive, full positive charge full negative charge. With covalent bonding, the atoms are sharing electrons. Okay, so when they share electrons, that's when they behave as a single unit. This is identifiable as a molecule in pure water. But in that cube of sodium chloride, these are ions attracting one another purely by Coulombic forces. You know, positives attract negatives. Okay, so the intramolecular bond that we're talking about here, we tend to focus on the molecular compounds only. We'll introduce ionic compounds into this mix when we start to make mixtures. Okay, I just wanted to make that distinction. When we say molecule, chemists mean covalently bound atoms in a single identifiable unit. And by the way, if that's the case, where do those elements come from in the periodic table? If they're going to be covalently bound, they all come from over here. They're all nonmetals. Right? Those are the ones that share electrons. When you get ionic compounds, you have one of these and one of those. Metal, nonmetal. Okay. All right, so those are intramolecular forces holding molecules together and by sharing electrons. The intermolecular forces, intermolecular, are the forces that hold those molecules together in whatever phase, in the solid phase, the liquid phase, or the gas phase. Now, the attractive forces that determine whether or not it is a gas, a liquid, or a solid. Okay? So those intermolecular forces, let's see, let me take this out of the equation right now. Those intermolecular forces come in basically two flavors. They can be dipole interactions. And water is a perfect example. Remember last semester we learned that the shape of water is what? Bent. Yeah, the word is bent or angular, like this. And we know that the polarity of the bond is like that, right? It's toward the more electronegative oxygen. But the polarity of the molecule then, since these are skewed like that, they add up to a polar molecule like that. Okay? So that means on this end of the molecule, we have a slight negative charge, and that's what that little delta means, slight. Not a full negative, but a slight. And then you have the positive ends of the molecules here to balance it out with two there. Okay, so when one water molecule encounters another water molecule, how do they orient themselves? Right? If they come at each other like this, right, there's repulsion. But if they come at each other like this, there's an attraction between this negative side and that positive side. Okay, that's a dipole interaction. Dipole of one molecule interacting with the dipole of another molecule. And in fact, this type of dipole interaction, water, is a special kind. It's the strongest of the dipoles. It's called hydrogen bonding. And as the name would have it, it has to have hydrogen bound to an electronegative atom, either oxygen, fluorine, or nitrogen. That gives it an extremely polar bond, extremely polar nature to the molecule, and that causes a very strong interaction. That's why water is a liquid at room temperature and pressure. If it were not for this interaction, water would be a gas, and we'd be in huge trouble. No liquid water on the surface of the earth. Okay, so I've introduced the dipole and this special type of dipole, the hydrogen bond. The other flavor I was talking about is a weaker bond. Suppose you do have a non-polar molecule. And the example I use is nitrogen. Now, nitrogen, like this, that's the Lewis dot structure. Nitrogen is, this is an element, but it's still a molecule. Right? You can have molecular elements. It's a diatomic element, but it's also a molecule. We could do other things also, but this is a good example. Is this polar? No, it can't be, because these are the same element. They have exactly the same electronegativities. Their distribution of electron density is equal between both of them. It's a perfectly covalent bond, triple bond actually. So, but how do we know that there's anything attracting the nitrogen molecules together? Well, at room temperature, nitrogen is what? It's a gas, right? You're breathing it right now. Okay. If you cool it down, cool enough, you can make it condense into a liquid. So how does that happen? Think of it this way. The intermolecular bonds are stronger for solids and not as strong for liquids, but they're still there, and almost non-existent for gases. Okay, so the stronger intermolecular bonds, if you have a molecule that's a solid, the bonds are fairly strong, holding it together in that solid form. And liquids are a little bit weaker, but they're still there, holding it in that liquid form. Right? So if we can liquefy nitrogen, what's holding the nitrogen molecules together? Because there's no dipole. That's the second flavor. Not dipole-dipole. These are called London dispersion forces. London dispersion forces. Named in honor of its proponent. I forgot his first name. His last name's London, obviously. Okay. So these forces are always weaker than those. Much, much weaker. And we can tell by melting points and boiling points. You've got to get nitrogen down to minus 195 degrees C in order to turn it into a liquid. So that means you've got to reduce the kinetic energy of the molecules in that substance so that they don't overcome these forces because they're so weak. Okay? That's the clue that we know that these forces are weak, because you got to get it so cold to make it liquid. Okay. So the other difference between these two is that these are permanent. They're always there, based upon the molecule's polarity of bonds and their geometry. Okay, these are temporary. They come and they go in an instant. So how does that happen? Well, electrons in the bonds and the unbonded pairs are not static. They don't just sit there. Right? They're in constant motion. And what happens is they tend to, on a very short time scale, congregate on one side of the molecule or the other. Okay? So when they do that, in this case, if this one develops a slight negative side and this one a slight positive side for just a nanosecond, any nitrogen molecule close to it is going to feel that change, and it's going to do that. because this negative accumulation on this side pushes electrons away from that side, and this side attracts them. So we get this accumulation of electron density over here and over there. Now you have opposite charges and they attract. Okay? And like I said, that happens for an instant and it's gone. Now, while these forces are temporary and these are permanent, London dispersion forces are always there. They're always present. Whether or not they're significant is the question. If you have a molecule that has a permanent dipole, then the London dispersion forces are so weak they don't even matter. You can ignore them. But if you have a molecule that's not polar, then they become significant. All right. Now, I spent a lot of time on the first two slides because this discussion needs it. Hydrogen bonding. All right, we can go back to that and talk about hydrogen bonding. Why is hydrogen bonding so much stronger? Well, one of the reasons is the hydrogen. Right? What is that hydrogen? That hydrogen is a proton, right? And you know how small protons are, I think. So what that means is, with this added electronegativity, this is simply a proton with its electron being shared here. And with this increased electronegativity on the oxygen or the fluorine or the nitrogen, giving it a strong polar nature to the bond. Also, with this proton being so small, this other oxygen or nitrogen or fluorine can approach very close. And the strength of attraction between two opposite charges is dependent upon what? The size of the charge and the distance between them. Okay, so if we can get that distance down very small, then they're closer together and the strength of attraction is much, much greater because of that. Okay. That explains hydrogen bonding. Okay, which are stronger, intramolecular or intermolecular forces? Which one's stronger? Yeah, oh, that's right. Excuse me. Intra, right. The bonds that hold molecules together. Yeah. And it only makes sense, right? What if it was the other way around? What if the intermolecular forces, these were stronger than the ones holding the molecule together? They'd rip the molecules apart. It wouldn't stand a chance. We wouldn't have any molecules, right? Okay, so it makes perfect sense that the ones holding them together have to be stronger. The covalent bonds, the ionic bonds are much stronger than the dipole-dipole interactions. Or even if you get water and you want to put an ionic compound in there, now you've got these ions floating around. So now you've got those attractions. Those are dipole ion bonds. Right. And they're very strong too. Right. So we know that the intramolecular bonds are stronger because they hold the molecules together against these other forces. All right, so I'm going to have to start moving along here a little bit. Think of phase changes. I alluded to this already. Think of phase changes as an interaction between the intermolecular bonds and the forces trying to disrupt them. And those forces are manifested in several forms. Major is temperature. Right? Remember the kinetic molecular theory. Right? Molecules are always in constant motion, which means they have kinetic energy. So if we increase the temperature, which is a measure of the average kinetic energy of the substance, if we increase the temperature, then we increase the kinetic energy. And when they slam into each other, that energy may be high enough to disrupt these bonds that would attract them. So the higher the kinetic energy, the higher the temperature, the more difficult it is. I wanted to get the shared screen on the back also. Okay. So when a substance changes from solid to liquid to gas, the molecules remain intact. We've already established those intramolecular forces are very strong, and they won't be disrupted by physical means. So these changes in state are traced to the forces among the molecules that hold them together. But we need to make some more room here. All right. So this is just a visualization of what you have with a solid. Right? We know that solids can hold their shape and they have a definite volume. Liquids have a definite volume, but they don't have a definite shape, so they need a container. The reason for that is the forces holding them together that would make them a solid now are disrupted enough so that they can slide past one another. So they're still close enough to maintain their volume, but they're not close enough to hold their shape as a solid would. And then, of course, gases are at the extreme, I guess this one, extreme. The kinetic energy of the molecules in a gas is so high that nothing is going to hold them together. In fact, the ideal gas is one in which the molecules are treated as independent units. Remember that from our gas laws and the kinetic molecular theory of gases. You can't hold them together. They don't stay together. There's lots of space between them. That's why two or more gases mixed together make a perfect solution every time. There's lots of room. Now, when they deviate from ideal behavior, there has to be some attraction or repulsion involved between the molecules. But for all intents and purposes, we can treat gases at room temperature and near 1 atmosphere pressure as ideal. In other words, they don't interact. All right, so when we go from solid to liquid, we add energy. And the motion of the molecules increases, their kinetic energy increases, and it's sufficient to disrupt that regular structure that you would see in a solid. Liquid to gas, we're still adding more energy. Now, when you go from a liquid to gas, we can also influence the transition from liquid to gas by external pressure. If we decrease the pressure on a liquid, then we can move that liquid into the gas phase with less energy. So that becomes, when you go from solid to liquid, pressure doesn't matter. But when you go from liquid to gas, external pressure does matter. So we can decrease the pressure above the liquid, and we can make it boil at a lower temperature. Right? So you can boil water. That's why it takes 4 minutes to boil a 3-minute egg in Denver, because it's a mile high and the air pressure is lower. So you can't get the water hot enough. It boils at a lower temperature. But it's still that interaction of the molecules with one another, in the intermolecular forces that hold those molecules together in the different phases. Generally speaking, when you go from a solid to a liquid to gas, the density decreases. All right, so if you look at, remember the formula for density, mass per unit volume. So if we fix the mass and hold it constant for a fixed amount of solid, and we're changing the phase, then we're going from solid to liquid. And generally speaking, when you go from solid to liquid, you're moving the molecules a little farther apart so they can get past one another. So we're increasing the volume. So the density then for a solid should be less than the density for the liquid. Because with the solid, the volume, solid to liquid, the volume is increasing. If you increase the denominator, then the quotient decreases, correct? Okay, so that's why the density decreases. Oh, excuse me, the wrong direction. The density decreases. Yeah, the density decreases for a liquid. And then for a gas, it decreases way, way, way out there. Because you've increased the volume of that mass to like 1,000 times. On average, go from a liquid to a gas, the volume increases on the order of 1,000 times. That's just a rule of thumb. It varies. Okay, that's for most materials. Water is an exception. And that's what this table shows. The density of the liquid water is greater than the density of solid water. Right? Ice is less dense than water. Everybody knows that. Otherwise, your ice wouldn't float top of your drink. Icebergs wouldn't float. When water turned from liquid to solid, if it got more dense, it would sink to the bottom of the ocean and stay solid. And it'd just keep forming solid, 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 solid until the whole ocean was solid ice, top to bottom. And then we'd be in trouble again. Now, a quick explanation. If this is true for water, right, we go this direction for water, the density of ice is less than the density of the liquid water. The reason for that is that if the density decreases for ice, that means the volume has to increase. So how does the volume increase for the solid? It has to do with the way the water molecules arrange themselves in the solid. Right? In a liquid, water molecules are like this. Right? They're just like that, all over the place. In the solid, what happens is those water molecules arrange themselves in a regular structure. Right? Instead of being close together and just far enough so they can move past one another, in the solid, water forms a regular crystalline structure that is more open. It adds space. Right? And you know what shape that is. It's a hexagon. And then you put your extra here. Well, I'm not going to waste your time with that. But see, it adds that space in that hexagon. And we know it's that shape. Why? How many sides does a snowflake have? 6. That's based upon that structure. Right? Ice forms that hexagonal structure. Right? So that explains why water bucks the trend. It should be greater than. Solid should be, let's see, liquid should be less dense than solid, and gas is less dense than liquid. And the other way around is for water, liquid is the denser. Actually, it goes through a transition about 4 degrees C. You get a transition. Actually, the density of liquid water is maximum at 4 degrees C. And then as it approaches 0 degrees C, it starts to form those hexagons. That's enough of that. We're running on fumes here, so let me go to all right, just to summarize, dipole-dipole bonds are between molecules that have a polar nature. So if you got two molecules, if you got a pure substance, a pure molecular substance, and it has the molecules have a dipole moment. Right? We know how to do that. Then they can experience the dipole-dipole forces, holding them together. The strength of the dipole-dipole is roughly about 1% of covalent or ionic bonds. Now, for hydrogen bonding, it's much stronger than that, but on average, 1%. Right? We talked about the hydrogen bonding. You need nitrogen, oxygen, or fluorine adjacent, attached to a hydrogen molecule in order to do that. So we don't just need pure hydrogen and oxygen, or hydrogen sulfur, hydrogen nitrogen, or hydrogen fluorine, right? We could do that, right? Hydrogen fluoride, for instance. But if you have a molecule that's even bigger, like ethanol, right? You know, the drinking kind, right? You have a methyl group out here. Well, y'all haven't had organic chemistry yet, so let me be. You have your methyl group, and then you have this one like that. Then you have an oxygen, and then you have hydrogen out here, right? You have the potential for hydrogen bonding there as well between ethanol molecules. And if you even have a very long molecule out here, let's see, we say we have butanol, which has 4 carbons. Right? You still have the potential for that hydrogen bonding among those molecules. Okay? So this can happen. In fact, you can get hydrogen bonding interactions within molecule, as long as the molecule is big enough to fold back on itself. Right? And the extremely large molecules like DNA, right? They depend upon these dipole-dipole and hydrogen bonding interactions for their structure. Proteins do, carbohydrates, they all depend upon these intermolecular bonds for their structure. But that's for another course, actually. So these London dispersion forces are very, very weak, but they do occur in all molecules at all times. So the trend is, if the intermolecular forces are increasing, if we increase the intermolecular forces, they increase. What effect does that have on these other measurable physical properties? Melting point. If we increase the force holding things together, it takes more energy to pull them apart, right? So you have to increase the temperature. So the melting point increases with increasing intermolecular force. Same thing with boiling point. It takes more energy to pull them apart. So the boiling point is also going to increase. This is an example of what we call a homologous series. And in this case, we're looking at a group. If you follow the trend lines here, let's look at the bottom one. That's the one that's most consistent, the carbon group, right? So you look at carbon, what members, what elements are in its group? Carbon, silicon, germanium, tin. So if we form hydrides of that carbon group, we get CH4, which is methane. Then you go down to silicon hydride, or silane, they call it. Germanium hydride or tin hydride. All of those follow this trend. So the boiling point is going to increase as the molecule gets bigger. Why is that? Well, look at the structure of methane. We did that one, right, last semester. What's the structure of methane? It's a tetrahedron, isn't it? Connect those points like that. It's a tetrahedron. It's a regular structure, and the polarity is very weak among the bonds, right? But even if it was a strong polar bond, they would be regularly arranged, and that geometry would cancel all of them out. So these hydrides of the carbon group are all nonpolar. Okay. All right. Now hang on to that idea. As you go from carbon to silicon to germanium to tin, what's happening to the size of the molecule? You're going from period 2, 3, 4, 5. They're getting huge, right? The molecules are increasing in size. All right. That's important because with an increase in size, those London dispersion forces become more significant. Why? Because when you're spreading electrons over a larger area, you have more probability for the electrons to unevenly distribute to one side or the other. So the bigger the molecule, or the bigger the atom, in fact, the higher, the stronger the London dispersion forces. So as these molecules get bigger, you'll see that their boiling point increases. Right? Boiling point increases because the intermolecular forces are increasing. So that's what we should expect from nonpolar molecules like that. Well, the other groups like the pnictogens, right? Nitrogen, phosphorus, arsenic, antimony, or the halogens, fluorine, chlorine, bromine, iodine, or the chalcogens, the oxygen group, oxygen, sulfur, selenium, tellurium, we would expect them to follow the same trend, except the problem is their polarities get in the way until the molecules get really big. Right? So the bigger molecules, like, for instance, tellurium dihydrogen telluride, which is the analog to water, H2O, H2TE, is the bigger one. So it follows that trend, as does the one with selenium in it, the one with sulfur in it. But once you get to the smaller molecules, now you've got the ability to invoke hydrogen bonding. Remember, nitrogen, fluorine, oxygen, right? Very electronegative atoms. Plus, you can get those molecules really close together. So that's where the trend is bucked, right? Instead of going down from, we're using the chalcogen group. Instead of going from H2S to H2O down here, which would be the trend, right? Water should have a boiling point around minus 80 degrees if it followed that trend, but it doesn't. It has a boiling point of 100 degrees. And it's because of the introduction of the hydrogen bonding. Okay. So which molecule is capable of forming stronger intermolecular forces here? Nitrogen or water? Water, of course. Right? I spent half an hour talking about that a minute ago, a half hour ago. Right? So water has the stronger force because of its hydrogen bonding. Right? How about this one? Notice the difference here. We have a formula unit of C2H6O. Right? We don't know what the structure is because the molecular formula doesn't tell us that. It could be the one on the left. Right? It could be, yeah, it could be this one. Ethanol. But it also could be dimethyl ether. Different structure, same molecular formula, different structure. Notice what effect that has. This is only slightly polar, right? Look at the Lewis structure here. What you've got is this oxygen with these lone pairs and these methyl groups down here. So you do have slight polarity. You have a little bit of polarity, but this one has the hydrogen bond. So this one is going to have a higher boiling point because the intermolecular forces are stronger. Okay. So which of these gases would behave more ideally under the same conditions of pressure and temperature? Remember ideal behavior? Think billiard balls. Ideal behavior in gases is where the gases behave as if they're just chunks of matter that bounce off one another. No interaction whatsoever. So which one of these would have the least interaction among the molecules? This one or this one? The least interaction will be that one. That's completely nonpolar. London dispersion forces are all it has to work with. This one, though, is slightly polar toward the oxygen. Right? Remember the trends, periodic trends? I was just going blank. Electronegativity of oxygen is greater than carbon, right? It's to the right of carbon. So oxygen has a greater electronegativity. This has a slightly polar bond. So the more ideal behavior is going to come from the nitrogen. All right. So characteristics of liquids, well, that they obviously lack rigidity. They have a higher density compared to gases, and that's consistent over all materials. They have very low compressibility. We used to think that liquids were incompressible. That is, you could push on them just as hard as you would push on a solid, and they would not change their volume at all. But we know that's not true now. Right? Laboratory experiments where we compressed liquids and actually measured their volume change show that they do compress. So there is some space between the molecules that we can take up by pushing them harder together. We've also taken samples of seawater at depths of a mile, 2 miles deep, and found that the density down there is much greater for water than it is at the surface. So as far as liquids go, we're looking at various, let's see, did I skip something? Surface tension. I left that one out. What is surface tension? Well, liquids have this, they still have enough attractive force to hold them together into that definite volume, just not enough for the shape, right? So that force that's holding the liquid together, it has to be in a container. So you got your liquid here, and you got molecules at the surface, and you got molecules down here also, right, down here in the liquid. Well, when they're attracting one another, as they do, to maintain that liquid state, these guys are attracting, right? They're attracting in all directions. But at the surface, they can only attract in this direction and those directions. Right? So the total force of attraction is the same for the surface molecules as it is for the body molecules. But since the surface molecules don't have anybody above them to attract to, they have to spend that attraction on molecules next to them. So they have you see a stronger attraction at the surface of the liquid than you do in the body of the liquid. And that accounts for surface tension. Surface tension, by definition, is the resistance of the liquid to an increase in surface area. So how would you increase the surface area of this liquid? Well, dump it on a table or dump it on the floor and see if it spreads, right? That would increase its surface area, right? Some liquids, like mercury, When you drop mercury on the floor, it just like it's very high surface tension, bulbs up like that. Or some plastics, right, in liquefied form. If you drop them, or say maybe silly putty, you drop it, it goes like that. Well, that's not a bad example because it's kind of solid. But liquids do that too. And liquids that don't have very high surface tension, like oils, very, very thin oils, like, well, all right, let's use gasoline, for instance. Right? What do you see if you have a gasoline spill? You see pretty colors, don't you? It forms a very thin layer and refracts the light. So you see, depending on your angle, you see different colors. Well, it spreads out. It really spreads out a lot. Whereas water doesn't spread out as much. They have different surface tension. Where else can you see surface tension? So my first degree was in biology. And one of the topics we studied was invertebrates. Spineless creatures like insects or I don't know, earthworms, right? They were all over the ground after the hard rains we had recently. That drives them out because there's oxygen depletion. They come out to the surface. But these insects, go back to the insects, there are certain types of insects that take advantage of surface tension, right? Their density is such that if they were in a tight little ball, they'd sink, right? They're more dense than water. But if they have these big feet, 6 of them obviously are insects, they spread them out, right? And everywhere their feet touch the surface of the water, you see it kind of dents. The water's dented. They're taking advantage of that surface tension to hold them up on the surface of the water, called water skimmers. And you'll see their feet moving really fast and they go right across the water. If they put their feet too close together, then the weight that's on that exceeds the surface tension of the water and their foot drops in. So they have to spread them out. All right, that's surface tension. Surface tension also says that when you blow soap bubbles, they always form a sphere because a sphere has the smallest surface area for volume of any geometric shape. All right. Capillary action is another thing we observe in liquids, and all of these physical properties that we can define and observe in matter are traceable to these intermolecular forces. Capillary action. What is capillary action? Well, if you have a tube like this, and we're going to stick with water for now, right? You have water, and it's a really wide tube. What are you going to see? Water level is going to be right there. Right? If we go down to the microscopic level and look at what's happening within the water and interactions between the water and the glass, we find that there is attraction between the glass and the water. Okay, these are cohesive. Well, these are adhesive forces, excuse me, adhesive. When you have forces that are holding unlike materials together, those are adhesive forces. That's why tape is called adhesive, because tape is not your skin. And cohesive forces are those intermolecular forces that hold the molecules together in the liquid form, right? So you've got a battle between the forces within the substance and between the substance and its container. Well, when you have a wide tube like that, you don't have enough surface area interacting with the giving you the adhesive forces to pull any of the water up the surface of the glass. But when you make the tube very thin, now you got a smaller volume contained within the glass, and the surface area now of contact allows adhesive forces to win over the cohesive forces holding the water down. So you get this drawing up the sides of the tube like that. And that's why when you look at when we use volumetric glassware, where do we measure the mark? It's at the bottom of the meniscus. We call that curve that forms the meniscus, because there's a traction on the sides of the walls that pulling the adhesive forces are fighting the cohesive, pulling the water molecules to the glass. Well, these forces now are pulling the water this way, but the surface tension doesn't like it. It doesn't like, because when you go from here to here, you're increasing the surface area, right? So now the cohesive forces are saying, all right, we're going to pull back this way, right? So we pull back that way. Well, the adhesive forces are pulling again. So it keeps happening. Until when? Until the forces balance. Right? So the adhesive forces now are drawing the water up the capillary, and the cohesive forces are opposing it and drawing the water up like that. But when the water is drawn up like that, right, by the surface tension, what's it fighting? It's fighting gravity. So it goes only so high, and then now the forces of gravity are opposed to the surface tension that is pulling it together against the adhesive forces of the water against the sides of the tube. There's a balance that's reached. So the smaller the tube, the higher the water goes, right? Because when you have a smaller diameter over a length, right, that's less mass. So you can move higher before you have the same amount of mass you did with a bigger tube. So the smaller capillary allows water to move higher. Now, that was water. When you put mercury in a tube, you get the opposite meniscus. You get a convex meniscus. That's because the cohesive forces in the mercury are stronger than the adhesive forces holding it to the glass. So when you use a mercury barometer, we don't have one here, but there's one in Lewisburg. When you read that mercury barometer, it is calibrated for the top of the meniscus. So in this case, the cohesive forces exceed the adhesive forces. Let's see. All right, and for water, of course, it's the other way around. The adhesive forces exceed the cohesive forces. All right, that was capillary action. Now, another property of liquids that is affected by intermolecular forces is viscosity. Everybody knows what viscosity is, right? What was the commercial? I don't know if they show the commercial anymore for ketchup. Was it Heinz ketchup? Hunt's ketchup, right? Their ketchup, if you pull the top off and you turn it upside down, it doesn't come out. It's too thick. Yeah, it's very viscous. Viscosity is a measure of a liquid's resistance to flow. So if you put your honey in the refrigerator, supposedly to keep it from molding, I'll address that in a second, then it gets colder and less viscous. So you can take the cap off of your honey, turn it upside down, and nothing happens. You can store honey at room temperature. It will not spoil. Now, it may crystallize. All you have to do is heat it up in, hot water bath, and it'll go back into solution. but it will not spoil. Two reasons. When bees collect nectar,
Damn.
when bees collect nectar, what do? Well, they take the nectar back to the honeycomb and they put it in the comb. And then before they seal it over with wax, what do? They spit. They spit in it. They spit an enzyme into it. And the enzyme takes the sucrose in the nectar and turns it into invert sugar, which simply breaks the two molecules apart. That's part of sucrose. And you get fructose and glucose. Right? What that does, and we'll learn that in chapter 11, I think, is it increases the number of moles of dissolved solute. If you increase the number of moles of dissolved solute, you increase the osmotic pressure. We'll have to define that for you later. But what that does effectively is if any bacteria or fungal cells fall in that stuff, they're quickly dehydrated. It just sucks the water right out of them. Nothing can grow in honey. All right. So this viscosity is dependent upon the intermolecular forces. As the intermolecular forces increase from one substance to another, the viscosity increases because the forces holding them together keep them from flowing. In other words, they're trending toward the solid nature. They're more viscous. All right, now let's switch gears to solids. We've subdivided solids into two groups. The amorphous solids, and the crystalline. Crystalline solids. Morphos is a Greek root that means shape. So A means not. They don't have a shape. What that means is they don't have any regular order to their structure. Right? Perfect example of that is glass. Glass is an amorphous solid. Most glasses. There are some specialty glasses that are crystalline, regular crystalline structure. But for most parts, glass is an amorphous solid. Crystalline solids have an ordered structure and can be divided into the smallest unit that reproduces itself in space. Okay, that's called the unit cell. And that's where we're headed with this discussion, talking about unit cells.
Every other Monday.
There are two ways to describe
This Monday and next Monday, and then after that it's every other Monday.
Is a three-dimensional repeating unit. Right? So once you know the unit cell, you can describe any size of the crystalline solid just by repeating that unit cell. The other way of describing them is called the closest packing structure. And the best way to think of that is if you got balls next to each other like that, that's the only way that they can arrange each other in this linear structure, just touching one side. If you get another set of them, you can either touch them like this, right? And then they touch like that. So they're touching here like that. You got this space in here, okay? Or you can just shift them over a little bit and let them fall into these cracks. And that uses up that space a little more efficiently. That's closest packing.
That is so pretty.
What? What's pretty?
Oh, the snow on the mountain.
Snow. Oh, we're talking
Yeah.
chemistry.
I'm driving. I'm on my way there, and I just come across the snow on the mountain. I'm sorry. I didn't know I wasn't muted.
Well, no, I mean, it's true. It is pretty. Now, as long as you don't have to drive through it, it's beautiful. So these two methods, the unit cell and the closest packing structure, are related to one another. There are two ways of describing crystalline structures. So they're like cousins. But sometimes the characteristic, one way of describing something is easier to solve problems than the other. So that's where you make the distinction. All right, so for the unit cell, there are many types of unit cells. We're going to focus on just 3 types. Simply because we don't have the time or the need for any further discussion. Right? There are whole chemistry courses that devote themselves nothing but that. So one type of unit cell is the simple cube, or let's see, they give it another name. No, simple cube, that's fine. So the simple cube, so we can draw our cube like this, right? Been doing that since grade school. There's our simple cube. Now, where do the atoms go? Well, if we use small atoms so that we can see the relationship, then we put them at the corners of the cube. Okay. That's a simple cube. Okay. Now, if we draw more cubes, we put a cube out here, a cube there, cube in back, cube in front, cube up here. Okay. So there'll be cubes all over the place, expanding infinitely. That's what that second row, the lattice network. It's got the arrangement. So these atoms would be part of the next cube, right? They would be shared. But the unit cell itself looks like that. Now, the space filling model is closer to reality, the bottom one, where this one is touching that one. And this one is touching that one. Right, I didn't draw it very well. But that's the space filling model, and that's really what's happening. So those corners of the cube are occupied by, we're going to keep it simple. We're going to occupy them with metal atoms. Okay. The next possibility is the body-centered cube. Body-centered. So we still got our cube right here. And we've got atoms here at the 8 corners. But we've also got one right in the center of the body. Okay. And the space filling model shows you that now, because this guy's in the middle, and this one touches all of these 8 corner occupied atoms, that now they can't touch each other along the edge of the cube. See, there's space there. All right. And the last one we're going to look at is the face-centered cube. The face-centered cube, of course, starts with a cube. It also has atoms at the corners, right? But it has an atom on every face. Back, on the side, bottom, top. So it's 6 faces on a cube, right? Right, you roll the dice. How many choices you got? You got 1, 2, 3, 4, 5, and 6. 6 faces on a cube. So we've got these faces are occupied by, and the body centered is gone. Now we only have the face centered. Okay. And by placing these on the face, we're now, this face centered atom is touching these 4 here. All right. I think I got a video.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next two examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
A lot of that stuff toward the end is added material. I mean, I'm not going to hold you those details. What I want to point out is, first of all, when we go from simple to body-centered to face-centered, we've got more atoms represented by that unit cell. This one, the simple cubic, we've only got 1 atom per cell. That's not very efficient. In the body-centered, we have 2 atoms per cell. It's a little more efficient. And then in the face-centered cubic, we have 4 atoms per cell. That's much more efficient. So efficiency increases from left to right. And when we talk about the closest packing model, which is coming up next, that's the only reason I wrote these in here. When we think of the layers that we're packing, the ABA, if you have a layer of atoms here, and then you shift it so that you can set down in the grooves. And then the next layer, you shift it so it sits down in the grooves there, but those grooves, this atom layer matches first layer. So it's ABA. You're seeing the same position, relative position of the third layer to the first layer. That's why it's ABA. In the face-centered, we get a more efficient packing in which the A layer has a B layer on top shifted to fit some of the holes. And then with the C layer shifts to fit another set of holes. But the next layer, the 4th layer, looks like the A layer. So that's why it's ABCA. And there's more to come. So, right, just... Could be, yes. Yeah. I'm no expert. I'm struggling here. All right, so let's digress just for a moment to discuss the experimental verification of these unit cells and the way that they're layered together. Right. And we're going to talk about this father and son team, Bragg, father and son team, and what they determined experimentally and proved was their Bragg equation. And their Bragg equation simply says that this whole number integer, 1, 2, 3, 4, 5, whatever it happens to be, times the wavelength is equal to 2 times the distance between the layers times the sine of theta. Now we have the angle of incidence of the reflection. They're using X-rays here. They're firing X-rays at a crystal structure, and they're noting where is the peak emission on the other side. Okay, so I think I've got a diagram here. There we go. So notice what we've got here is 2 layers of atoms, right? There's a layer and there's a layer. So the top layer acts like a reflector, and the bottom and the next layer acts like a reflector. And what you get is the reflected rays that come off of the crystal are either in phase, completely out of phase, or only slightly out of phase. And what you get as a consequence of that is either constructive or destructive interference. We talked about that last semester. Constructive interference is where when the waves come back out, how do they combine? If the hills and valleys match, we've got perfect constructive interference. If the hills and the valleys are exactly opposite, you have perfect destructive interference. So what you're looking for as a practical matter is when you have the X-rays bouncing off the surface and penetrating the crystal and then coming back out at the same angle, right? This is the law of reflection. We're going to have physics, optics. The law of reflection simply says that the angle of incidence equals the angle of reflection. Okay? That's why when you're standing in a mirror, if you move this way a foot, it looks like you move 2 feet in the mirror because you're superimposing the other angle. Anyway, so this angle that they're using here is the angle of approach to the surface. Right, so that's theta there. I used to use this to investigate clay structures in soils. And it was very effective at determining the difference between one type of clay and another type of clay. I won't go into the details. It's just there's the practical application for this. Well, if we can determine the distance between the layers, we can say something about how they're packed together. Now that's on a 2-dimensional scale. That's the way I used it. Right? If you want to know something about the crystal structure of a more complex crystal lattice, then you need a 3-dimensional image. And that's where it becomes very complex and requires lots of training and experience to interpret your diffraction patterns. Right? In fact, this is the method that was used to determine the double helix structure of DNA. Right? And it took a long time. The main problem with DNA is that it's an amorphous solid. They had to figure out how do we get it into a crystal array so that the X-ray diffraction will work. And that was the assistant. I can't remember her name. She was a research assistant for Watson and Crick. And she did all the legwork for their Nobel Prize. Unfortunately, she died of breast cancer at a young age. I mean, actually, even before the Nobel Prize was awarded. So I don't know what the personal dynamics there were, but it wasn't unusual for researchers to have lots of people working under them, and they're at the top, so they get the awards. I mean, that's the fate of every graduate student. Okay, so we can interpret the crystal structure by looking at the X-ray diffraction pattern. All right, so now let's go back to types of crystalline solids. I hate to erase that. I'm not going to unless I absolutely have to, because there's lots of good information here. An ionic solid, right, is one like table salt, where you have an array of cations and anions in a regular crystal structure. And it depends on two things. One is, what's the charge on the ion? Is it a +1, +2, +3? Or the anion, is it a -1, -2, -3? That is determined by the ions that are bound together. Like all the alkali metals are going to be +1. All the halogens are going to be -1. So anytime you combine an alkali metal with a halogen, you're going to get a 1-to-1 ratio. If you go to the alkaline earths, the second column, they're all +2. So if you combine them with halogens, you're going to get one of those for two of these. So they're always going to be X, let's see, M, X2, right? M for the metal and X for the halogens. The ratio is going to be two of these for one of those. If you go, say, to aluminum, it's a +3, and combine it with one of these, it's going to be 1-to-3. So that ratio is one of the things that determines what type of structure that the ionic solid is going to, what lattice it's going to use for the most efficient arrangement of its anions and cations. Molecular solids are a little different. These are covalently bound molecules at each of its lattice points. Think diamond, right? Diamond. If you could shrink yourself small enough and you could stand on one of the carbon atoms at one side of the diamond, let's say it's a perfectly cut diamond, there are no flaws. Then you could jump from one carbon atom to the next, assuming that that carbon was covalently bound to the next, you could jump to each one to the other side, and you'd still be in the same molecule. That's a molecular solid. Atomic solids, well, that's one type of molecular solid, let me put it that way. Atomic solids are those in which the atoms occupy each of the lattice points to describe the structure of the solid. I think metals, pure metals. Okay, so here we have an example of diamond, which is, let's see, here we go. Covalent bonds holding the diamond together, ionic bonds holding the ionic solid together, and hydrogen bonds holding the ice together. Okay, so this comes straight out of your textbook. Classification of solids. So the atomic solids, one example is metals. They have a delocalized covalent bond. Actually, that's an oversimplification. We're not going to spend a lot of time on those right now. Network atomic solids are those in which the covalent bonds each of the atoms to one another. Diamond is your perfect example there, and that happens with non-metal atoms. Another type of atomic solid is formed from the noble gases. So you could make, let's see, liquid argon is really easy to make. I used to use tanks of this stuff, liquid argon. And as you get bigger, you can make solids of these, right? Because the London dispersion forces become greater. So these molecular solids then have either dipole, or London dispersion forces. And then the ionic solids we discussed already, they're discrete ions that are bound together. And many of them occupy usually one of these two types of arrangements where you might have usually the anions are the bigger parts. So they would occupy the corners. And then you would fit into the spaces the cations. Okay, so now we're going to switch gears to the closest packing model. And I've got a video coming up, and I'll forewarn you, that it's narrated by an Indian woman. Not a Native American, I mean, a subcontinent Indian. So adjust your hearing to her accent, and then it won't be so difficult to follow. But the closest packing model, and we're going to use metals for our example here because they're the simplest to deal with. We assume that the atoms are uniform hard spheres. Right? We're not going to say anything about variations in their attractive forces. We're treating them as uniform hard spheres, and they're packed in layers. All right, so here we go.
The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice, and its unit cell is primitive cubic unit cell. Dimensional close packing from 2-dimensional hexagonal closed pack layers. The 3-dimensional hexagonal closed pack structure can be obtained by placing 2-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a 2-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are 2 types of voids: tetrahedron voids denoted by T, octahedron voids denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the 4 surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the 6 surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A type and the second layer as B type, then the third layer will also be A type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close-packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
Every time I watch this video, I learn something new. And learn some of the things that I assumed in the past were wrong. So what I learned was that with the layering designations as A, B, or C, you could have ABCA, or you could have ABA from either one of these. The coordination number would be 12 for either one, whether it was covering the tetrahedral voids for the ABA or covering the octahedral voids for the ABCA. So I'm not going to hammer you really hard with this, but I do want you to have an appreciation for the stacking of layers that gives you different efficiencies. Okay, so let's go to closest packing arrangement of these uniform spheres, the ABAB packing, where the second layer is different than the first, but the third layer is like the first. That's what we're saying with ABAB. And the relationship between this closest packing model and the unit cell model is such that we should see hexagonal closest packing, giving us well, it says a hexagonal unit cell. Now, now it can even be confusing for me, so I can't expect you to be any more enlightened than I am, unless you have a comment that would help. But the relationship between these two cousins, right, the unit cell and the closest packing model, are, I would assume, tenuous. So what do they mean by when you say hexagonal closest packing gives you a hexagonal unit cell? What does that mean? Well, think of the geometric structure they're trying to describe, a hexagonal. If you describe a hexagonal unit cell, then there should be 8 sides to it. In the cubic cell, of course, you do have 8 sides, but the hexagonal has, let's see, 1, 2. No, there are only 6 sides. Cubic. Hexagonal has 8 sides. So there's the difference there between the cubic model and the hexagonal unit cell in the HCP model. This one switches to ABCA. So if you go to ABCA, now you're talking cubic closest packing rather than hexagonal closest packing. It's the difference between cubic and hexagonal closest packing. With the ABC model as the face-centered cubic is its unit cell equivalent. All right, so if we look at it this way, with ABA, what is it going to give us? Well, they're telling us that hexagonal closest packing still gives you a face-centered cube where you have ABA. But if you go to ABCA, you're still going to end up with a face-centered cube. And that's why I think that this is important, this coordination number. Each one of those atoms, any one of those atoms can be touching 12 other atoms in the cell. All right, so what does that mean for problem solving? Let's see, here we go. I've already covered that. How many atoms are represented by each of the unit cells? This one, of course, where it only has the edges covered, and there are 8 other cells that claim part of that atom. That is 1/8 for each one of these. So 8 times an eighth is 1 atom for that cell. 2 atoms for the body-centered cubic and 4 atoms for the face-centered cubic are represented in that cell. All right, and this just illustrates it. Come on. Right, A represented by one metal atom. Actually, the animations leave out this one. This one is actually 2 atoms per cell for a body-centered cubic, because that atom belongs to this cell only, whereas these belong to 8 other. This one has 8 other cells, 8 other. All right, for problem-solving purposes, what we need to know is what's the length of that edge of the cube. If we're going to use this unit cell model, then what's the length of that edge? Because if we know the edge of a cube, we can find the volume. And if we know which one it is, we know how many atoms are represented by that volume. So that's our doorway into determining, say, density of metals. if we know how many atoms of a given metal are in which one of these unit cells, then we can work that back toward, say, density as a problem solution. Well, the simple cubic cell is easy, right? These guys are touching each other. So all you need halfway there is the radius of the atom, and halfway on this side is the radius. So 2r is the edge of that cube. That was easy. The rest take a little geometry, and I don't have time to go into it right now. I think I do have in Brightspace, I have additional documents that describe how these others are determined. Face-centered cubic, this one. Face-centered cubic, yeah. The length of the edge is the radius of the atom times the square root of 8. Okay, and the body-centered is a little more complicated. The radius of the atom times 4 divided by the square root of 3. That will be the length of this edge. So that gives you the ability to determine the volume of the cube if you so desire. So here's an example where we want to calculate the density of silver metal. Okay. And we're saying it's a cubic closest packed structure with a face-centered cube as the unit cell. Right? We're actually given the cell edge as 409 picometers. So we didn't have to go through the gyrations of what's the atomic radius of a silver atom and then determine what's the edge. So this problem, whoever wrote the problem is kind enough to give us the edge of the cell. 409 picometers. Now, what's a picometer? Okay, I'm going to have to start erasing stuff. Remember what a picometer is? What's a pico times anything? Remember your prefixes? Maybe you don't remember that. I'm sorry? Yeah, 10 to the negative 12 is a pico. All right. So this is the density that's determined experimentally, 10.5 grams per cubic centimeter for silver. So if we've got a face-centered cubic unit, we know we have 4 atoms per cell. So with 4 atoms of silver, we can determine what mass that represents. We can also, since we know it's 409 picometers on a side, we can determine the volume of the cell. So we've got a handle on mass, we've got a handle on volume, we can determine the density. So the second step here goes to the volume of the cell. So 409 picometers cubed is 6.84 times 10 to the 7th picometers, and this is equivalent to cubic centimeters. So if we did, let's see, is it going to work that out or just give it to you? No, it's not. It's going to work it out. So if we had 6.84 times 10 to the 7th picometers, was it? Cubic picometers? Yeah. We want to convert that to cubic centimeters because density for solids is in grams per cubic centimeter. So you need a conversion factor, picometer. I don't know if I can go to cubic centimeters with picometers. Let's say, I'm sorry. Could be. I know meters, right? 10 to the minus 12 meters. And then I have to cube that, right? It used to be cubed. And then I can do meters to centimeters. That's the way I would do it. So 100 centimeters per meter, and then we have to cube that also. Okay. So that's supposed to give us the 6.84 times 10 to the minus, 10 to the third. No, 10 to the minus 23rd. Cubic centimeters. Now for the mass, we know we have 4 atoms. This is the volume of a unit cell. Now we want to know what mass is in that unit cell. So if we have 4 silver atoms, right, our avenue toward mass is molar mass. So if we have 4 silver atoms, how many moles of atoms does that represent? 6.022 times 10 to the 23rd atoms per mole. That's how many moles of atom. So what's the mass per mole of silver? Now you have to go look it up. It's 107.87. 107.87 grams per mole. Okay. So that's the grams per unit cell. And I think I've calculated that one right here. Eventually. So that's no, we didn't calculate it. We just went ahead and did it all in one single calculation. Let's do that. 4 enter 6.022 6.23 divide. And then 107.87 times. So this is 7.165 times 10 to the minus 22 grams. So what we need is grams per cubic centimeter. We need grams divided by 6.84 times 10 to the minus 3 cubic centimeters. And that will give us 10.5 grams. So we calculated the density based upon what we know about the unit cell of silver. And it agrees with the experimentally determined density of silver. You're not impressed, right? You know, what practical use is that? Who cares what the density of silver is as long as I have a ton of it, right? I don't know what's the price of silver these days. $35 a troy ounce, something like that. You know, if you have a ton of silver, you got a lot of money. I mean, everybody thinks about gold, but silver is valuable too. Okay, so let's go to what is it that holds metals together? What are these intermolecular forces that hold them together? Well, originally, the electron C model was proposed. And it's just that. There's a sea of electrons, the valence electrons of the metal, that are circulating, and the cations of the metal are spotted in that sea. Right? That seems reasonable, but it doesn't explain much. What we need is an ability to get a handle on the energies of the electrons that are in that sea. And that's where the molecular orbital model comes in. I never thought you'd see that one again, did you? This is the electron C model. Right? I'm not going to spend much time on that because it's defunct. But remember, in the molecular orbital model, all of the electrons of every atom in the chosen chunk of matter go into the molecular orbital array. All of them. And what you get is a new set of orbitals, molecular orbitals versus the atomic orbitals. The molecular orbitals now are where the electrons reside. Well, as it turns out, the molecular orbital energy levels for metals, if you have more than a dozen atoms, they start to get really close together. Those molecular orbitals, they're sitting very close together. And I think I've got a picture that helps understand. Here we go. So notice the more atoms that the more atoms with their atomic orbitals that you're feeding into the molecular orbital model, the closer those orbitals, the molecular orbitals get. Until when you have a mole of them, they're virtually continuous. Now what that does is it allows easy transfer of electrons from one orbital to the next with just a little bit of energy bumping them. Right? So when when you have a group of metal atoms, what you're going to find is that there is a very narrow band at the top, which is filled, the filled molecular orbitals. Let's see. I'm trying to think of the acronym for those. LUMO, that's it. Lowest unoccupied molecular orbital. Would be on an energy scale here, would be, say, at this level. And then the highest, lowest, oh, excuse me. It's the other way around. The lowest unoccupied molecular orbital is here, and the HOMO is the highest occupied molecular orbital. So you'd have electrons here. Okay, and the gap between these two is very small. So a little bit of energy like that, and they can go anywhere from there. They can go over here and then come back down. What we're trying to do is explain physical properties of metals based upon this model. Because if the HOMO and the LUMO are very close together, then a little bit of energy will move those electrons into a mobile region. So that's why thermal conductivity, electrical conductivity are very high for metals. In fact, the highest thermal and electrical conductivity of any other metal in the periodic table is not gold, it's silver. Silver is the best conductor of heat of any of the metals. Electricity too. The problem is for power companies, the price of silver is prohibitive, right? So that's why it went to the next best thing, copper. And actually it went even below that. We only use copper at the local level inside your homes. But for transmission of power across great distances, they use aluminum. It's so much cheaper. And they've developed technologies for the transfer cables that will allow efficient transfer of that energy. That's another course. Okay, so these metals, we can fit them into a crystal lattice. And we're going to make what we call, actually what are homogeneous mixtures of metals, we call alloys. Solid solutions. There are two types. One type of alloy is where you have atoms of the solvent metal replaced by atoms of the other. You just take out one of your atoms and put in one other place. Those are called substitutional alloys. Example of that is brass, where you substitute nickel for copper. The other is called interstitial alloys. These are where you have those voids that we saw in a previous video. You have those voids, and the voids now can be occupied by very small atoms. And it doesn't take many of them to change the physical properties of the alloy. And the best example of that is steel, where you have iron atoms here, and in the voids, you have carbon atoms. Carbon atoms are very small compared to the iron, so they fit right in the voids. And what they effectively do is they keep, because under shear force, these layers can be shifted, right? You can push them. But if you put a carbon atom in here every now and then, say down to, I don't know, 0.1% or less, right? Actually, 0.1% is high carbon steel. Much less than that, then you can keep those layers from shifting. All right, so there's your copper zinc substitutional alloy, and there's your steel made of iron. Pure iron, by the way, you can scratch it with your fingernail. It's that soft. You can't do that with steel. Here's I don't know if we talked about this. I'm pretty sure we did early on. Allotropes of elements. Remember what an allotrope is? It's the element. It's the same element, but it has a different structure. And I use diamond as an example of one allotrope of carbon, graphite as an example of another allotrope of carbon. The diamond, of course, is a four-dimensional lattice and a tetrahedral structure of carbons covalently bound to each other. Whereas graphite is a hexagonal plate layer of carbon atoms, and the things that hold them together are intermolecular forces. The intramolecular forces hold the hexagons together, and the intermolecular forces hold the layers together, and they're much, much weaker. So what's a practical use of that fact? Well, graphite is a very efficient lubricant. We call it a dry lubricant. Right? We normally think of lubricants as liquids like oils, waxes, or greases, right? But one of the things that greases can do is they're kind of like wet water. They pick up dirt. So if you use grease and the bearing is not sealed, it'll eventually get clogged up with dirt and just grind away at your ball bearings and just eat them up. So that's why when we use bearings in modern cars, those bearings are sealed. But I used to be a dirt biker, and we would lubricate our cables with graphite because graphite didn't attract dust. We just squirt some graphite down the cables and made them run real smooth, and didn't add that extra problem to in introducing dirt, which in this case would be soil-derived aluminosilicates, and they're very hard, and they just grind up metals like nobody's business. Okay, so here's the difference between diamond, which is bound by those covalent bonds, and metals, which are bound by the molecular orbital bonds, where the energy difference between the LUMO and the HOMO are very small for metals, but for diamond are very large. So how does that manifest itself in physical properties? Well, one of the ways is in thermal conductivity. Right? Metals conduct heat very efficiently. So if you put something hot against a metal, it'll cool down very fast. The conductivity is very high. If you put that against a diamond, it won't conduct heat. Right? And you can use that to measure the differences among gemstones. So when you take a gemstone to a jeweler and I don't know, you want to appraise it, say, well, they want to find out what it is. Right? And one of the ways is they put this special device on it that tests the gem's thermal conductivity. The very highest thermal conductivity there is diamond. So if they put this device on diamond, it's going to have the lowest thermal conductivity. Let me say that again. The very lowest thermal conductivity you have is diamond. So when they put this device on diamond, it has a very low value for thermal conductivity. And I may have told you this story before, but that's how we determined that my wife's friend who gave her a gemstone, and all we had to do was pay for the shipping. It was supposed to be a tanzanite, a blue tanzanite, right? So we took it to the jeweler to show it off, and they said, "Oh, it's a lovely blue diamond." I said, "What?" Yeah. Says, "Let's check it." So they got their device out, they put it on there. It had low thermal conductivity, just like a diamond. Said, "You've got a blue diamond there." Said, "Okay, you guys keep it, send it off, have it appraised, and give us the documents so we can put it on our insurance." Because we weren't expecting a diamond. I think her friend made a mistake. Well, we notified the friend to keep it. guy's wealthy. Anyway, now what we see with graphite, because graphite, we showed you the gross anatomy of graphite as those hexagonal plates laying on top of one another, and they interact only through intermolecular forces. And since graphite is nonpolar, what we've got is London dispersion forces, very weak forces holding those layers of graphite together. So that's, did you ever wonder why lead pencils, right, by the way, they're not made of lead, they're made of graphite with a little bit of wax to hold it together, why they can adjust the hardness of the lead? Well, pure graphite is very weak. I mean, if you had a pencil lead made of pure graphite, you just touch it to the paper and it just crumble. So they have to put some wax in there to hold it together. Well, the amount of wax they put in there determines soft and hard lead. And of course, the forces they use to compress it together. Anyway, this goes back to I think the last chapter of last semester, where we talked about these overlapping unused p orbitals that would form this pi system above and below the layers of carbon. And that stabilized them so that the individual graphite layers are very stably covalently bound. But between the layers are very weak forces. Now, is this the last? Look at my hard copy. Let's see, let's check. Yeah. We still have a little bit of discussion to go on chapter 10. Ceramics. Everybody has a sort of an intuition about what ceramic is. What's a ceramic? Have you ever made ceramics? You start off with clay, right? The slip, right? You pour the stuff into your mold and you let it sit for a few minutes until it absorbs into the mold. And then you pour the rest out and it holds a layer of it, right, on the thing. And then you let it dry further and it sort of shrinks away from the, I can't remember, do you use a releasing agent that you spray on the casting?
I don't use the casting, I use the pottery wheel.
Oh, okay, you throw your own. Okay, I cheated. I used a mold. Well, once you get to the point where you've got where it holds its own shape, then you can crack the mold open, or you can take your thrown pottery, and then you let it air dry further, and then you decorate it. Or you fire it once, and then you decorate, and you fire it again. Sometimes they go through several firings. But what you're doing is with that clay that's not very strong, when you fire it, you change its crystal structure. It's still a solid, right, in both cases. But now you've changed the structure in such a way that it is very strong against compressive forces. Right? But it's not strong against I just went blank again. Against shear forces, right? Shear forces like it would experience if you dropped it on the floor, right? It would shatter, right? Ceramics are brittle, but they're very strong against compressive forces. And they're also very resistant to heat. So many of the industrial chemical reactions that are conducted in ceramics that are specially treated to resist the chemical action of the compounds that are in this reactive state. They call them refractory. That is, they don't react. So So those are ceramics. Ceramics are, generally speaking, they're operationally defined. If it satisfies these conditions, it's a ceramic. And they can be dense, or they can be not so dense. I mean, for instance, the tiles on the space shuttle and the heat-resistant tiles that are placed on many of the rockets, like Elon Musk's Starship, those big black hexagonal tiles, they're made of ceramics, but they're very, very, very low density. And they don't conduct heat very well, and they insulate the underlying metal. So we'll move on. Semiconductors. What's a semiconductor? To understand semiconductors, go to the metalloids. Remember that black line that separates the metals and well, in this case, it's a red line that separates the metals from the non-metals. So very close to that line, you have sometimes behave like metals and sometimes like non-metals. Well, these are pivotal in the semiconductor industry. And probably the major one is this one right here, silicon. Silicon is dirt cheap to mine. I mean, just go to any beach and you just got tons and tons and tons of the stuff. But the real cost comes with the semiconductor industry in purifying that silicon. Silicon must be virtually pure, no impurities whatsoever, in order to make it work properly. So you can go to the internet and Google pure silicon production. And what you'll see is they draw silicon out of this reactor in a big, we call them ingots. A big ingot about that big around and about 12 feet tall. And then they put it on their slicer and they slice thin layers of it. All right, so that's where you get your wafers, and that's where the business of making a semiconductor starts. We do what's called doping. In other words, we sputter other elements into the silicon, and it changes the behavior of the silicon from silicon, which is relatively non-conducting, to partially conducting. Now, if it's an N-type semiconductor, what we do is we dope it with an element that has one or two more electrons than silicon does. So those electrons now are free to move. And so we're making an alloy, so to speak, at the atomic level. Using, say, arsenic or phosphorus, which has one more electron than silicon does. So now we have this N-type semiconductor with this free electron that can move around. Only it's not like a conductor, like you would have a copper wire. It moves freely. It moves when you give it enough push. So that's where the control comes in. Or the P-type semiconductor, where you dope it with an element that's left of silicon, like aluminum or gallium or indium. So it has one less electron, and you create what they call the hole, a positive void in the matrix. And for convenience, we say the hole moves, right? It's positive. Actually, the holes don't move. It's the electrons that move, and they leave a hole behind, which means if the electrons are moving this way, the hole's moving that way. So we combine these N and P semiconductors in such a way that we can produce logic gates, like which is true, which is false, which you have to choose. And we can control whether they're open, closed, or whether they stay that way. And that's where the control and the semiconductors become powerful, because now we can say that this is a 0 and that's a 1. Now we have a language, a binary code that we can impose on the semiconductor and solve problems with it. Right. There's an example of the N-type on the left and the P-type on the right. All right, let's see. We're not going to go into a lot of detail here. This is just, so when we have ionic solids, what we find is that we have cations and anions in a crystal lattice. And characteristics of those solids are such that they are very, very stable. And they have very high melting points. You can melt table salt, right? And some engineering applications do that. They turn it into a liquid. It has a very, very high heat capacity. It can hold lots of energy and transfer from one place to another. I assume it's extremely corrosive, actually, when you have those free ions floating around. But it takes a lot of energy to get them into that liquid state because the electrostatic forces holding those ions together are extremely strong. And in fact, the strength of the ionic forces are based upon what I told you earlier, is that what is the size of the charge, the amount of the charge, and what's the distance between the charges. That determines the strength of the bond. So here are two examples. Sodium chloride, and these are relative sizes of the ions. Sodium on the left is blue and chlorine is green. And magnesium and oxygen. So magnesium oxide versus sodium chloride. Well, what you notice is two things. One is sodium is single charge, chlorine is a single charge, magnesium is a 2+ charge, oxygen is a 2- charge. So you've got one difference there is the size of the charges are different, right? Greater charge size between magnesium and oxygen gives them a stronger Coulombic attraction. But also the size of the ions are smaller. Right? O2 is much smaller than Cl-, and Mg2+ is much smaller than sodium. So those ions can get closer together. So they have a much, much stronger attraction. What you would expect to see in their melting points, magnesium oxide would have a very, very much higher melting point than sodium chloride. Okay, now with these ionic solids, and this goes back to the Indian lady's description of the holes. If you're only having 3 balls in this arrangement, you've got a trigonal hole. Right? That's the only possibility for 3. You got that trigonal hole. And this is for ionic crystals, these holes are too small for most cations. So those holes are never occupied. If we place another ball over that trigonal hole, we get a tetrahedral hole. So examples here are zinc sulfide. So who occupies what? Well, typically speaking, the anions are bigger than cations. Why? What happens when you add an electron to an atom? It goes into the next highest orbital, doesn't it? So it expands the size. So that's why negative ions get bigger from their neutral state, and cations get smaller because they lose electrons. So when you have zinc sulfide as your example, who's going to occupy which sulfide or zinc is going to occupy which? Sulfide is going to occupy those blue balls, those positions. And the zinc is going to fit in the tetrahedral hole. As it turns out, it is small enough to fit in that hole. So here's the octahedral arrangement. The hexagonal closest packing. So we have these 3 different spheres forming that octahedral hole, right? And that was covered in the video also. So if we compare the size of the holes, of course, I think this is really not fair. I'm just going to show you anyway. Because a trigonal hole is two-dimensional. The tetrahedral and octahedral holes are three-dimensional. But the size of the trigonal hole is small, right? Because it's only in one layer. The tetrahedral hole is a certain size, but the octahedral hole is bigger. So the octahedral hole is going to be able to accommodate a larger cation if it's available. Right? If the anions occupy those octahedral positions, then you can fit a larger cation in the octahedral hole than you can in the tetrahedral hole. This comes straight out of your book, so I'm not going to hammer this one. Now let's talk about some physical properties. In fact, you're going to need to know something of these physical properties for our next lab. First of all is vapor pressure. We talked about some of those liquid characteristics like surface tension related to intermolecular forces. These also are related to intermolecular forces. But first we have to describe our terms. What we mean by vapor pressure. If we have a vessel and we put a liquid in it and cork it, first thing that happens when you cork it now are that liquid atoms some of them have sufficient energy to transition into the gas phase, the vapor phase. Right? Remember the energy profile of any substance is not a single temperature dictates all the kinetic energy for those molecules. It's an average. So if you look at the temperature profile of let's see, temperatures here, and this is numbers of atoms, then it's going to be more like a bell-shaped curve. Most of them are in that region. Some of them are here, low energy, and some of them they're high energy. So you've got a few of these high energy that have enough energy, they can move into the vapor phase. Right? That's one of the reasons you can spill water on your arm and it feels cool. Or that's why we sweat. Because some of the energy, some of the atoms or molecules have enough energy to vaporize, and that takes heat. They draw heat away from you as that source. Well, when they take away their energy, the bulk shifts this way, and it draws more energy from any source it can. And that's from your skin in this case. Okay, back to this one. So initially, they all move from here one way into the vapor phase. But eventually, you build up enough of them in this one. So now, some of them have lower energy as they exchange energies. They have low enough energy that they start returning. Some of them return. So at some point, you got an equal rate of condensation versus evaporation. And when that rate is equal, going both directions, then there's a stable pressure here at any given temperature. Right? If you increase the temperature, you're going to change that value. But at a given temperature, you develop a pressure inside here. That's the vapor pressure. It's an equilibrium situation, a physical equilibrium. This is just another way of expressing it, and we don't have time to stop there, so I'm going on. What you'll notice on the macroscopic level is the volume will decrease, and then at equilibrium, it'll stop. Now, what we see on the outside is no movement. But on the macroscopic level, the activity is furious, going both directions. And this vapor pressure is characteristic of a couple of things. One is, what's the nature of the liquid? What are the intermolecular forces holding it together? Right? So if the intermolecular forces are very high, like for water, at a given temperature, vapor pressure is going to be low. But if the attractive forces are very low, like for dimethyl ether, then the vapor pressure is going to be very high because the forces holding it in the liquid phase are low. And at the same temperature as water, there's enough energy to eject a lot of that stuff into the vapor phase. So what's the vapor pressure of water at 100 degrees C? Well, if it's boiling, the vapor pressure is 1 atmosphere. That's what 100 degrees means. At 100 degrees, water's boiling, the vapor pressure is 1 atmosphere. Here's another way to determine the vapor pressure and show the difference is to compare a true barometer on the left with the vacuum at the top. And that will measure 1 atmosphere as 760 or 760 millimeters of mercury. If you put water up in that space, just a little bit of water, then enough of it will vaporize to decrease the height of that column by 24 torr, 24 millimeters of mercury. So the vapor pressure at this temperature is 24 torr. If you put ethanol up there, which vaporizes more efficiently, has a lower intermolecular force attractions among the molecules, then it's going to be 65 torr. And I'm assuming this is at standard temperature, like 25 degrees Celsius. And if you have diethyl ether here, which is mostly what's used, the dimethyl was my original example. Diethyl ether is the kind they used to use to anesthetize people when they operated on them. If you do that, then it vaporizes so efficiently because the intermolecular forces are so low that it will produce a vapor pressure of 545 millimeters of mercury. So the only thing that's changed here is the nature of the molecule that produces that vapor pressure. Okay, so this is an expression of boiling point, right? The boiling point of diethyl ether is about 30, not quite 35 degrees. Right, so you can put it on your hand and it'll boil. Right? What's the Celsius temperature of body? 37. 37 degrees Celsius is 98.6. So you could put some diethyl ether in your hand. I'd wear a glove though. And it would boil in your hand. Ethanol though, no, it won't. 78 degrees. And water, of course, is 100. Now, what we're going to talk about now is the Clausius-Clapeyron equation. And it's derived from this relationship of intermolecular force to vapor pressure. Well, we can quantify that intermolecular force based upon the amount of heat required per mole to vaporize that material. Right? It's called the heat of vaporization, the enthalpy of vaporization. Right? Remember H, enthalpy? So what it's saying is we're going from liquid to gas. Right? 1 mole. And that's the amount of heat required in joules to vaporize it. And it's related by this Clausius-Clapeyron equation. The original equation was like this one at the top, right? But that's not very useful because it's got a proportionality factor A in there that you have to determine experimentally. So what we need is one like our before and after equations, where if you know what it is before and you know after without one variable, then you can solve for the missing variable. And that's where we're going with this one. We go to this solution here. We have the natural log of the vapor pressure at temperature 1 divided by the vapor pressure at temperature 2 is equal to the expression on the right, the enthalpy of vaporization divided by the gas constant. And this gas constant R is the one with joules in it, 8.3145, I think it is. And then the term that you multiply that times is the inverse of temperature 2 minus the inverse of temperature 1. So that formula, if you know the two temperatures and you know the vapor pressures at those two temperatures, then you can calculate the enthalpy of vaporization. Or it's like any other equation. If you know all the variables except one, you can solve for it. You know, take your pick. All right, so there's the Clausius-Clapeyron equation. And remember, temperature must be in Kelvin. How do we know? What's R? R is joules per K mole. Right. If the constant multiplier here has temperature in K, the variable's better be in K. Otherwise, it won't work. So remember how to make K. Just a reminder. C plus 273 equals K. Right, your K temperature, Celsius temperature plus 273 is K. All right, for this example, say we have the vapor pressure of water at 25 degrees is 23.8 torr, right? We saw that in a previous slide. And the heat of vaporization at 25 degrees is 43.9 kilojoules per mole. So we're given that part. What's the vapor pressure of water at 65 degrees Celsius? Right, so now instead of enthalpy being the unknown, the second temperature being known, we want to know what's the new vapor pressure. Right, so we go back to the original equation. So we're actually solving for this vapor pressure right here under the second temperature. So we put 65 plus 273 here, 25 plus 273 here. We have our R value there, 8.3145. And we have the delta H of vaporization, which was given as 43.9 kilojoules. There's another problem. Check your units. That's kilojoules per mole. What's the constant? The constant is joules per mole. Right? So how many joules in a kilojoule? 10 to the third, 1,000. So it's 43.9 times 10 to the third joules per mole. That goes into that equation as the delta H right here. All right, if we do that, then we should end up with 194 torr, or 194 millimeters of mercury, is the new vapor pressure that we would expect. Okay? Those are the types of problems that, well, not all of them, but some of them, that you'll find in the review document for this chapter. In this case, there are 2 review documents, 1 for each chapter. And there are 2 worked problems, 1 for each chapter. Okay, this heating curve of water is here to illustrate what's happening. As you add energy to water, where does it go? What kind of work does it do? If it starts off here at minus 20, and it goes up to 0 and plus 20, and then we go on up to maybe 100s up here. It's temperature, temperature in degrees C. And this is heat versus time. So we're steadily adding heat over time. So what happens at first? Well, down here, of course, well, let's see, that's not right. I meant to put 20 at the bottom. So let's put 20 down here, 0 here, 20 there, and then 100s up here. So what you're starting off here at minus 20 degrees C is you're heating up the solid, the water. Water at minus 20 degrees. All you're doing is adding energy so that now you're increasing the vibration of those atoms in the solid. And you reach a point where there's enough energy that you've added so that now you're turning your solid to liquid. And at this point, all the energy you're adding to it is breaking those solid to liquid, solid bonds to make a liquid. And that's why the temperature remains constant until all the solid is gone. Now that all the solid is gone, you start vibrating those liquid molecules until they're fast enough to make a gas. So we heat them up. Let's see. We're going past 20. We're going past 20 to 100. Right? And over time, that energy is used to vibrate the liquid molecules. And once you reach 100 degrees, you've got enough energy now that you're moving, you're boiling the water. So at any point in that body of water, there's enough energy to convert it from liquid to vapor. Right, so you're going to see the bubbles form probably from the heat source at the bottom of the pan. So once you go from, let's see, here we have solid only, here we have solid with liquid, and here we have liquid only. Now we have liquid and gas together. Okay, once you've converted all the liquid into gas, which is where the energy is going now. All the energy is being put in. That's why the temperature remains constant. As long as you've got liquid and gas together, it will remain constant. Once all the liquid's gone, now you're superheating the gas. Right? And that's the way energy is transferred in many factories. Superheated steam. And it carries a lot of energy with it. Okay, so now we only have gas. We call that a heating curve for water. Call it a phase change diagram if you want. It's okay. Any questions? I haven't stopped to ask questions, but stop me anytime. Something doesn't make sense. And if I can answer it, I will. All right. Okay. Which of these should be larger? We've defined this delta H of, let's see, which one was it? Vapor pressure. We defined this one, right? That one. Enthalpy of vaporization. So that's going from a liquid. This goes from a liquid to gas. How much heat does it require? This one is one that we haven't described. Enthalpy of fusion. Fusion refers to melting point, going from solid to liquid. So the enthalpy, the amount of energy per mole of solid to produce a mole of liquid. That's what this one means. The question is, which one of these should be larger? Which one should have a larger value? Going from a solid to a liquid or a liquid to a gas? That right there. The heat of vaporization is much, much higher, often 10 times as much energy is required to make a gas out of a liquid than a liquid out of a solid. Because for this one, you have to completely break all intermolecular forces. There's nothing left. Here, you just have to weaken them enough and break some of them enough so that you can slide those molecules past one another rather than lock them into a solid shape. Okay. Now, that was one phase diagram that I showed you. There's another way to express phase changes that gives you a lot more information. And rather than define these terms, I'm going to show you an example. Here's carbon dioxide, but I'm just going to draw a generic. And what we have is Cartesian system, right? Where pressure is in this one, and we can just say it's in atmospheres. Okay, and this one is temperature. So we're actually comparing pressure versus temperature, and this is for any solid, any liquid, any gas, wherever you start in that diagram. It has lines. So as we increase the temperature and increase the pressure, what we have here is an expression of the phase boundary between gas on this side and solid on this side. This is a phase boundary. So you can cross it, you hold the temperature constant and increase the pressure, you can go from gas to solid. That. Or if you hold the pressure constant and the temperature increases, you can go from solid to gas. So for carbon dioxide, if this is 1 atmosphere down here, then you can go from 1 atmosphere, you can go from solid to gas, and that's called sublimation, right? That's what carbon dioxide does. Take a chunk of carbon dioxide, dry ice, throw it on the floor, and it'll just kind of steam until it's all gone. It goes directly from solid to gas. And then from this point, here, you can go out this direction, right? Or you can go this direction. And these are 2 more phase change boundaries. That's gas, that's solid, this is liquid. So at this temperature and this pressure, anywhere in here is liquid. And it goes out to a certain point right here. Stops. I'll come back to that in a minute. So all that means is, say if you hold the pressure constant at, let's see, we've got an example up there of about 73 atmospheres, right up in here somewhere, say 73 atmospheres. Then you can increase the temperature. If you hold the pressure constant there, you can go from solid to liquid to gas as you increase the temperature. Okay? Or if you have a temperature here and you increase the pressure, you can go from gas to liquid to solid. Okay? These are phase boundaries. Now, if you have a temperature and a pressure exactly at that point, you've got liquid and gas together at the same time. Or here you would have solid and liquid together at that temperature and that pressure. Or here you would have gas and solid together, right? At that example. There's one point on this graph where you can have all 3 phases together at the same time. And it's only at 1 temperature and pressure here. This is the triple point. There's one other interesting point. At this point out here, right here, this is the critical. They call it point. Yeah, critical. Anything above this temperature at that pressure, or at this temperature and this pressure, this whole region out here is a region that's occupied by a critical fluid. What that means is it is a fluid, right? It flows, right? It's not a solid. It flows like you would expect a liquid. The thing about it is, you cannot see whether it is a liquid or a gas. It's kind of a combination of both. And what you see in microscopic examination upon taking, say, liquid CO2, putting it in a vessel and putting it under pressure, as you increase the pressure, you can see it change. There's a phase where you have a phase, a liquid and a gas, separate phases. In that, you could look it up on the internet. Maybe I ought to insert that in here for effect. You see a different phase. You see a liquid here and you see a gas there. And as the pressure increases, you start to see that boundary disappear. And eventually, no boundary. Now you've got a critical fluid. We used to use critical carbon dioxide to extract metabolites from plant material, because it would go right through membranes, right? Like they weren't even there. plant tissue membranes. Go right in there, dissolve all the material, come right back out with it. And then all you had to do to recover the material, of course, was to remove the solid material from it, right? Take that extract and pour it over here somewhere, and then let the pressure off. And it instantly vaporized and left all your material behind, undamaged. Right? It was beautiful. Right? Up to that point, the way to get stuff out of plant materials like reflux it in methanol for 3 hours. Right? And there was always some heat damage. Right? But this way, it was completely pristine. And for some research, that's absolutely essential. But that's just a practical application. The other practical application is decaffeinating coffee. Right? Some of the best coffees are decaffeinated with supercritical fluids. They can get that caffeine out of there, no problem at all. Just sucks it right out. And then the carbon dioxide, you can recover it, recycle it, use it again. Or you can take all the carbon dioxide that Al Gore's jet is spewing into the atmosphere while he's going to his anti-environment conferences and, make use of it. How do you spell hypocrite? Okay. This is a phase diagram of water. Notice there's a major difference. I'm not going to draw this one on the board. There's a major difference between this one and the carbon dioxide. Notice the slope of this line right here, this blue line. On carbon dioxide, the slope is positive. Right? So if you hold the temperature constant and you increase the pressure, where carbon dioxide is concerned, you go from liquid to solid as you increase the pressure. But with water, since the slope of that boundary line between solid and liquid is negative, if you hold the pressure constant, you go from increasing pressure, you go from solid to liquid. That's unusual. Ooh, I missed some chats. Are the chat folks already here? Okay. Never mind. Okay. So this is just a test of whether you understand the effect of intermolecular forces on these various physical properties that we've mentioned. What happens to the boiling point as the intermolecular force increases? Boiling point increases. You've got stronger attractive forces, it takes more energy to get them apart. Boiling point, viscosity similarly. Right? Viscosity increases as intermolecular forces increase. Surface tension, same thing. As the intermolecular forces increase, the surface tension increases. Enthalpy of fusion, that is how much energy does it take to melt a solid, that increases also. Freezing point, right? That increases. Well, there. Vapor pressure. As the intermolecular forces increase, vapor pressure goes down because now you've got more force holding those molecules in the liquid phase. So the vapor pressure will decrease as the forces increase. And the heat of vaporization is like the heat of fusion. It also increases. So the only one that decreases with increasing intermolecular forces is the vapor pressure. The rest of them increase. All right. Okay, let's talk about properties of solutions. We're going to need to know something about solutions because our lab depends upon that knowledge. And I'll just say, anything that's a homogeneous mixture is a solution. Right? We discussed homogeneous mixtures early on last semester. So we can have different phases, right? Any types of gases mixed with one another, they always form a solution. There's no question. Air is a solution of 21% oxygen and 78% nitrogen and about 1% argon, and then some minor components. Antifreeze is a liquid in a liquid, right? It's ethylene glycol and water. And usually it's about 50-50 by volume. Any kind of booze is a solution of ethanol and water and some other things. So, solid solutions like brass, right? You can have copper and nickel. You can't just put them together and make a solution, right? Solids don't mix, right? So what you have to do is melt them. Mix them together, melt them, mix them, and let them solidify. Now you have your solid solution. Carbonated water is a gas in a solid. And by the way, when we talked about concentrations, we did define what a solute and a solvent was, right? Just as a refresher, right? The solute is the minor component, usually. And the solvent equals the major component. Now, there are exceptions, and we go by convention. If you make, say, sugar water for your hummingbird feeder, you start off with hot water, and then you add sugar to it. So we consider water the solvent and sugar the solute. But you can go 50%, which is usually where I stop for hummingbird feeder. By volume, 50% sugar and 50% water. You can go even higher than that. You can put a lot of sucrose in water to where you eventually have more sucrose than you do water, more solute than you do solvent, but we still say the solvent is water. Now, one characteristic is you can only have one solvent, one only. You can have many solutes. Okay. So now we're down to solids dissolved in liquids, like sugar solutions, seawater. Seawater is primarily the salt in seawater is table salt, but there are other types. There are magnesium, calcium. It has to be calcium. You know why? That's where coral gets their calcium to build their skeletons. Right? There has to be calcium in seawater. Otherwise, the corals wouldn't live. But strange as it may seem, we have solutions where the gas is dissolved in a solid. And the example there, hydrogen in platinum. Platinum is the catalyst for hydrogenation of unsaturated vegetable oils. Right? So if we add hydrogen to an unsaturated vegetable oil, I'm not going to draw the whole thing, but we've got at various places in the fatty acids in a vegetable oil, we have carbon-carbon double bond. Well, you just stick two hydrogens in there. Opens that bond up, and now you have here and here. That saturates, we say, saturates the bond with hydrogen. Well, they use platinum as a catalyst and hydrogen along with the oil, and they're intimately mixed so that what happens is the hydrogen actually dissolves in the solid, and it's there waiting for the fatty acid to come close enough and the reaction occurs. Same kind of thing happens in your exhaust system in your car, right, with a catalytic converter. Now, how do we express concentrations? Because if we have a solution, you know that a solution is a mixture, and mixtures can have variable composition. That is, you can have varying amounts of solute dissolved in a certain amount of solvent. So we need a way to express that. And the most common way is molarity. That is moles of solute per liter of solvent, of solution, excuse me, of solution. So this is very useful. If you have a value here, say you have 1 molar solution. If you had a big vat of it, 1 molar solution, and you pulled out 1 liter of it, you know that you have 1 mole of solute. And you can do something with it. All right. Another way to express it is percent by mass. So what we usually say is, remember the problem with percent. If you just write percent, it's a dimensionless number. You're not saying it has dimensions. It just says parts per 100. So it could be mass, mass. It could be mass, volume. It could be volume, volume. It could be mole, mole. Right? So in this case, we're saying it's mass solute per mass of solution. Right? So you need, I'm going to say grams of solute per gram of solution times 100. And that'll give you the mass percent of the substance. The next one is mole fraction. Mole fraction. And that's exactly what it is. It's a fraction. And we use this big X called a chi. That's the Greek letter chi. Anybody had statistics in here? Okay. You ever heard of chi-square? Okay. If you take statistics, you'll know it. Actually, some biology courses, that's when I was introduced to chi-square, it was biology course. Anyway, chi, this mole fraction is actually moles of solute, let's be consistent here, moles of solute per total moles. Okay. In our example, they would say moles of A and total moles of solution because you can have more than 1 solute. And it's a fraction. It will be less than 1. What would it mean if it were 1? If this value were 1, that means it's not a solution anymore. It's all solute or all that component, right? If it's 1. So if you have more than 1, or actually if you just have 1 solute, 1 solvent in a mole fraction. Let's say, for example, the mole fraction of A is 0.25. What's the mole fraction of B if B is the solvent? Yes. They have to add up to 1. Exactly right. The last one is little m, not big M, but little m, molality. Okay, what's molality? Molality is like molarity. It's moles of solute but instead of per unit volume, it's per unit mass. In this case, it's per kilogram of solvent. Rather than, it's not even kilogram of solution, it's kilogram of solvent. So it varies from molarity in 2 things. Instead of total liters of total solution, it's just a solvent, and it's not volume anymore, it's mass. Now, why would we want to do that? You know, isn't molarity good enough? Well, obviously not. If you're experimenting with a solution and you're interested in temperature change, what happens to volume when the temperature changes? It changes, right? So your concentration is no longer constant for that solution because the volume changes with temperature. So if you're experimenting in which the temperature changes, you want to use this one because you're basing it upon mass rather than volume. Mass doesn't change with temperature. So that's why we're going to use this one for our experiment, freezing point depression, right? And I'll describe what that means in a minute. Okay, so there's molarity, right? We're not going to stop there. Calculate a molarity of, all right, let's make some room here. Molarity of a solution that has 1 mole of sugar and 125 milliliters of solution. So we've got 1 mole, right? The units match, right? 1 mole of sucrose. Right, so that's good, right? Units. How about in the denominator? 125 milliliters. How many liters is that? Because we can't use milliliters. Right? It's the wrong units of measure. Change this to liters. Can you do it in your head, or do you need to do dimensional analysis? 125 milliliters. We need a conversion factor, milliliters per liter, right? Cancel the milliliters. How many milliliters in a liter? 1,000. 1,000 milliliters in a liter. So 125 divided by 1,000 equals 0.125. Actually, we've got a 0 out there too. So instead of that, we've got 0.1250. And just a reminder, right? If you write a decimal fraction and there's no 0 out here, it's wrong. I don't like orphan decimals. Okay, so now we got the right. 0.125 into 1 is what? I think it's 8. 8 molar. Yeah. So 0.125 inch is 1/8 of an inch. If you're using the English system. All right, how about this one? In this case, now we know what molarity is. We're given 10 molar equals what? What volume of this solution do you need to have 2 moles of sugar? So we've got 2 moles here. And our unknown is so many liters. Right? So if we solve this, I put this one over here and that one over there. X equals 2 divided by 10 equals what? 2/10, right? 0.20 liters. 2/10 of a liter. And most of our glassware is calibrated in milliliters, not liters. So how many milliliters is that? Right. To go from milliliters to liters, we move the decimal 3 places to the left, right? So to go from milliliters to liters to milliliters, and remember, if the units of measure get smaller, what happens to the number? It gets bigger, right? They go opposite. So we need to go to the right. 1, 2, 3. 200 milliliters. Right. I got this one. Okay. Now this problem emphasizes the fact that we're dealing with moles, not mass. So if we have sodium hydroxide, 100 grams, and we have potassium chloride, 100 grams. And we dissolve each in a different solution of 250 milliliters, final volume solution. What's the molarity? Is the molarity going to be the same? No. Why? Because the molar masses are different. And so we've got to change grams into moles. What's the molar mass of sodium hydroxide? Well, let's see, I have to add it up. 23 for sodium, grams per mole, 16 for oxygen, and 1.01 for hydrogen. That's grams per mole. So you add them up, 40.01. So if we multiply this times 40.01 grams, let's see, moles on top, excuse me. Right. Numerator, denominator have to cancel. So 100 divided by 40 is what? One hundred divided by 40.01. That's 2.499. 2.499 moles of sodium hydroxide. Per how many liters? Well, there it is again. All right. Get bigger, get smaller. 1, 2, 3. 0.2500 liters. So this concentration is going to be, let's see, how many places do I have? 4 decimal places. 9.998 molar. Okay. How about potassium chloride? Well, let's see, potassium, I have to look it up. 39.10 grams per mole. Chlorine, I got that one memorized, 3545. 5, 14, 74.55. So 100 grams converted to moles, right? Grams on the bottom, moles on the top. 75.55 divided into 100.
That'd be 74.55.
Excuse me, thank you. Yeah. Try that again. 100 divided by 74.55. 1.341. Yeah. 1.341 moles of potassium chloride. And then we're going to put it in 0.250 liters. Wait a minute, extra zero, there we go. 0.25. So I get 5.366 molar potassium chloride. Okay. So for the same mass of sodium hydroxide, we get a concentration that's almost twice as much as potassium chloride in molar terms. All right, so here we got, well, they rounded off to 3. 10 molar sodium hydroxide and 5.37 molar potassium chloride. So while we're here, that's the concentration of sodium hydroxide in solution. What's the concentration of ions? Right, when this goes into aqueous solution, what does it do? It's an ionic compound. It breaks apart sodium ions and hydroxyl ions, doesn't it? So the concentration of ions is double that. Right? It'd be about 20, a little less than 20 molar concentration of ions. I throw you a curve. If the concentration of the molecule is this much, the concentration of its parts, because it breaks into 2 parts, then the concentration of the parts, this would be 10 molar. This would be 10 molar. Add them together, you got 20 molar ions. That's important, especially for medical personnel. Well, it used to be when you had to make up your own solutions. Now they're pre-made, so those mistakes are less common. But if you know that you need an isotonic solution, a solution that won't cause your patient's red blood cells to either shrivel up or rupture, and you need to get the right concentration. Right? If you base it upon the concentration of ionic compound, then you're going to hit it wrong. Right? Because it's going to break up into 2 and actually double the ionic concentration, the ionic strength. How about this one? This one will be about 10.7, 11.4. No, 10.7, roughly. 10.8, something like that. Molar ions. All right. That'll be more important later when we talk about colligative properties. All right, what's next? Mass percent. Okay. So mass percent is fairly simple, right? We did mass percent earlier, right? Remember? Empirical formulas, molecular formulas from mass percent. Remember how to do those? No, if you're honest, probably no, that was more than 2 days ago. But it's based upon the same concept, only this is a solution. The mass percent we were interested in before was the percent of a component in a larger value. Right, so if we have a pure compound and the mass percent of carbon in that compound is, say, 10%, and the hydrogen might be 2%, and then some other element will be something. So the mass percent of the elements in the compound is what we were using. This is mass percent in a solution. So what's the percent by mass of a solution if percent mass, if we have 5.5 grams of glucose in 78.2 grams of water? 5.5 grams of glucose. What's the total mass of the solution? It's 5.5 grams of sucrose plus 78.2 grams of water times 100. So don't forget, if this says this only identifies the solvent, then you got to add the solute back to it for the total mass of the solution. And that should come out to be 6.6%. Mole fraction. Still copying? Okay. Mole fraction. For this, we need to know the total moles of everything in the solution. All the solutes and the solvent. And then we need to know the individual moles of each of the components in order to calculate this fraction. So here's an example. 8 grams of H3PO4. Let's see, mole fraction of H3PO4. So if we have 8 grams of H3PO4 and in 100 milliliters of water. So there's the solvent, there's the solute, and the mole fraction is going to be what's the total moles of water? The total moles of H3PO4 goes in the denominator. And then the numerator has only the moles of H3PO4. So we can do the moles of H3PO4, that's easy. All we need is the molar mass of H3PO4, right? So how about hydrogen? Well, hydrogen is going to be, do it over here, 1.01 times 3, right? Phosphorus, we have to look that one up, 30.97. 30.97 times 1. And then oxygen, we have 4 of them, right? 16 times 4. Add those up, and that's the molar mass of H3PO4. Okay, 3.03, 30.97 added to that. And then 16 times 4 is what?
64.
There you go. 98 grams per mole. So it's 98 goes right here. Divided into 8. And I get, let's see, 3 significant figures. 8.1 6 times 10 to the minus 2 moles of H3PO4. How about water? Right, we don't have a volume to mass, volume to moles conversion. So this is going to require first converting it to grams. And that's why we were given density as 1 gram per milliliter. So 1 gram per milliliter converts it to grams. That's 100 grams, essentially. Then we can convert grams to moles. So what's the molar mass of water? Got that one memorized? 16 plus 2 times 1.01. 18.02. So 100 divided by 18.02. 5.549. 9. Now we can do mole percent. So this is in the numerator, 8.16 times 10 to the minus 2 moles. And then in the denominator, the total, 8.16 times 10 to the minus 2 plus 5.549. And that will give us, so let me swap that around. Let's see. There. Add those together.
Zero point zero one four.
Yeah, I did something wrong. I'll take your word for it. I think yours sounds better. 0.14. You got another one? We got 3 significant figures here.
Well, 0.0144922.
5. 449. So it rounds up to 5. Okay, so there's the mole fraction of H3PO4 in that compound. Okay. About molality. We're going to use the same situation. So that's why I didn't erase that. Now we're going to calculate molality for this same solution. The mole fraction is 0.0145. And the molality now is moles of solute, which we have, kilograms of solvent. So we have 8.16 times 10 to the minus 2 moles of H3PO4. And then how many kilograms is 100 milliliters of water? Because now we only need the mass of the solvent. So 100 milliliters of water is 100 grams, and 100 grams is 0.1 kilograms. Is the, excuse me, the molality. Go. And then 0.1 divide. So this should be very simple. 0.81. 6. Yeah, 0.816 molal. Right? And it will be that value no matter what the temperature. That's another reason why paying attention to small letters and capital letters is essential in chemistry. The first reason is these symbols. Right? You write, let's say, if you write, let me take another. Yeah, find a good one. Oh, I can do that good. If you write C, oh, like that, what does that mean? That's carbon monoxide, right? If you write it like this, that's cobalt. Right? So capital letters make a difference in chemistry. And here's another example, big M or little m for concentrations. Okay, now we're talking a little bit of theory. Pull this out for a reason. How solutions form. We're going to try to use this information to predict whether a solution should form based upon the polarity of the solvent and the solute. All right, when we talk about a solution forming between one solute and one solvent, we're going to keep it simple. So you have the solute over here. You have the solvent over here. And you have the solution in the middle. So something has to happen. This is conceptually, right? All this happens simultaneously in the real world. But conceptually, what has to happen to the solute in order for it to form a new association with a solvent to make a solution? You got to break the bonds that hold the intermolecular bonds that hold the solvent, the solute together, right? So you have to, sometimes we call it, well, no, for this one, we call it, they call it expand the solute. I say break bonds. And I don't mean covalent bonds, I mean intermolecular. Intermolecular bonds. What does that mean in terms of energy? You have to put energy in, right? So it's an endothermic process. It's going to be a positive value. Solvent. Similarly, you got to break the bonds among the solvent molecules. Right? And this again is intermolecular. This is also an endothermic process. You got to spend energy, put energy in, and sometimes they call it make a hole. Make a place for those guys to go. Now, once you've got them separated from one another, then they come together and form new bonds. Form new intermolecular bonds. And this is always exothermic. Right? You come from here, form these bonds, give up energy. All right, so put energy in, get energy back. Let's see, I think for illustrative purposes, we call this delta H1, we call this delta H2, call this delta H3. And when you add those three together, this is the heat of solution. Right, that's what we actually observe in the lab. All right, so if you put energy, you put a lot of energy in, breaking those bonds, a lot of energy in there, and you don't get much back. Right? What's the overall result? Well, this is high positive, low negative. So this would be high positive. In other words, it'd be endothermic. Your solution would be cold. Right? So when you get a cold pack in the hospital and you break that capsule inside, slosh it around, it gets cold, it's that situation. Okay. In the other case, where it takes a little bit of energy to break this one, a little bit of that one, you get a whole lot back. That's exothermic overall. There for a minute, I thought I had a dry erase marker in my pocket with no lid on it. In that case, small, negative is very large. Delta H is going to be negative. This is an exothermic process, and that's the same kind of pack, only now when you break it and slosh it around, it gets hot. right? That's what that thing is trying to illustrate. All right, let's see. I've already explained what that is. This is an illustration of what it would look like on an energy diagram. What you're looking at is what's the overall energy, which is the green arrow. For the left one, the green arrow is big negative, right? Yeah, big negative. That's exothermic. Whereas on the right-hand side, it's a big positive. That's, let's see, left is exothermic, excuse me. Left is exothermic. Big positive is endothermic on the right. Okay. Now what we want to try to do is use this information to determine whether or not you even get a solution between two materials. Right, so if you have a material where you put in a lot of energy here, doesn't take much energy here, but you don't get much back either, then the probability and the heat of solution is going to tell you that the outcome is that you don't get a solution. So here it is laid out in a table. I think I pulled this out of your textbook. We're looking at this in terms of polarity. So I have to make some room here. That's kind of small, so that's why I want to write it up here. What are the possibilities in terms of polarity between solvent and solute? Well, they can have both. Let's see, they put them solute on the left, solute and solid. So if they're both polar, polar, or you could have non-polar. Let's see, I don't like the way they put those there. I want to put non-polar at the bottom. Non-polar at the bottom, non-polar at the bottom. So they can either be polar or non-polar. Or they can be polar solute and non-polar solid. Or they can be non-polar solute and polar solid. Now, what does that mean in terms of the delta H's? Delta H1, delta H2, delta H3, and delta H of the solution. Okay. If they're both polar, it's going to take a lot of energy to get these apart, right? Okay. So that means this is going to be very high. It's going to be high. Retard time. There we go. This is going to be high. Input. And what happens when they get back together? This one's going to be high negative. Right? So the difference here between putting in energy here, and getting a lot back is this is very small. Small delta H. And this solution forms. Okay. What about this one? Let's go to the bottom. Non-polar. This is going to be a low input of energy to get those things apart. Right? Because non-polars, what forces do they have available? London dispersion forces. Very small forces. So very low input here, very low input for the solvent. And the interactions between non-polars and non-polars is going to be low also. So you have low negative here. So the difference there is also small. Right? Small delta H of solution. And that solution forms. For this one, you're going to have a very high input for the solute. I input here. The solute, the solvent is going to be low. Right? If it's nonpolar, you're going to have a low positive input here. Well, what happens when they get back together? Low negative. They don't interact, right? Polars and nonpolars, they don't interact. So what's the difference here? Well, for polar and nonpolar, let's see, polar, nonpolar, you get a small delta H back. A small overall. Yeah, small overall. No, this is large. Large positive, right? Because you had to put a lot of energy in here, not much there. A lot of energy here, you got nothing back. So a large expenditure of energy to make the solution happen means the solution not formed. It's too energy expensive. That's what I'm saying. Takes too much energy to get that to happen. And the same thing can be said about this one, only now it's low positive here and high positive there. But it's low negative. You don't get anything back. And this again is large positive. And this solution will not form. Because you have to put too much energy in. It's too costly. So the solutions that form are between polar, nonpolar, and nonpolar, nonpolar. That's why the expression like dissolves like. Ionic and polar compounds dissolve readily in water, like ethanol goes into solution just lickety split. Sugars go into solution, no problem. Gasoline dissolves oils very easily. They're both nonpolar. Okay. So that's where that expression comes from. All right. So let's look at factors that do affect solubility, right? Because even though we say that the solution is not formed, that's a black and white statement when actually the solution will form, but it won't be very much of the solute in the solvent. Not much at all. You can increase that, right? Let's say the solvent is polar, water, and the solute is nonpolar, grease on your engine. You want to degrease your engine. So what do you do to this one? Well, it's going to take a lot of energy. So instead of using just water, not even hot water, you use steam. You put as much energy into that thing as possible. So when you steam your engine, you're actually dissolving the grease in the water as long as it's hot. But when it cools down, then the water rolls off and the grease is left on the concrete. Okay, so let's talk about solubility and other effects. Actually, not other effects. What are some of the effects on solubility of these particular items? I'm running out of time. Structural effects, polarity. What are the effects of polarity on solubility? Well, we talked about one already, so we don't have to spend a lot of time here. But we have terminology that may be important. Hydrophobic, those are non-polar substances. Hydrophilic, those are polar substances. Based upon water, that makes sense because water is polar. So if they're hydrophilic, if they love water, then they've got to be polar too. If they hate water, then they're non-polar. That's why oil doesn't mix with water. Or the vinegar and oil in your salad dressing doesn't mix unless you have something in there that force it. How about pressure effects? Pressure effects on solubility are reference to gases in liquids primarily. And this is Henry's law. Back in spell. Henry's law. So what it says is the concentration of the gas dissolved in the liquid is proportional to the pressure. And we need a proportionality constant of something. So as the pressure goes up, the concentration in the liquid goes up. Right? Think pop. Right? Carbon dioxide dissolved in water along with sugar and flavorings and that stuff. But what do you notice when you let the pressure off, when you crack the top? You hear a whoosh, right? The pressure is decreasing, so the concentration of gas in solution is also decreasing. Where is it going? It's going out the top, making a noise. All right. Now, a more effective, more useful form of that is related to our gas laws. Remember our gas laws? When we solve for the constant, then we have C divided by P, right? But if we change C, then P varies directly. And say this is after, this is before. So now we can ignore the K and say, if we know before concentration and pressure, and we know pressure after, we can calculate the concentration. That's Henry's law. And in this case, Henry's a last name. Kind of like O. Henry, the author. I don't even remember any of his works. O. Henry. So this is an explanation in terms of the kinetic molecular theory. Right? If you have these gas molecules above a liquid, right, up here, where's my pointer? Right here. And you increase the pressure by decreasing the volume, what are you doing? You're increasing the frequency of impact of the molecules on the surface of the liquid. And when you do that, more of them go into solution until equilibrium is reestablished. How about temperature effects? Well, in general, the temperature effects on solubility are such that in aqueous solutions, solids are generally more soluble in water as you increase the temperature. There are some exceptions, and they're not easily explained. There's some exceptions where increase the temperature and the solubility of the solid in solution goes down, decreases. Gases are very consistent. If you increase the temperature of the liquid in which the gas is dissolved, the gas becomes less soluble, right? And it makes perfect sense. If you look at it from the kinetic molecular theory perspective. So if you got gas molecules dissolved here, and you got some up here, and they're in equilibrium at this temperature, then if you increase the temperature of the water, right, temperature increase, what are you doing to the kinetic energy in there? Well, the kinetic energy of the liquid and the gas is increasing. And what happens to increased kinetic energy? It means more of these molecules are able to escape the surface. So that means the solubility of the gas in this solution decreases as you increase the temperature. And if you don't believe me, just look at boiling water. Actually, look at water before you boil it. Cold water on the stove, heat it up. What happens first? Along the edge of the pan, you start seeing these little gas bubbles. That's not water vapor. That's dissolved gas in the water coming out of solution as you heat it up. Eventually, right, you reach the boiling point of water, depending on your altitude. It's less than 100 here. Then you get the conversion from liquid to gas. But before that, you're actually degassing the water. Now, if you heat it up to where those little tiny bubbles disappear right before it starts to boil, then all you have to do is pour that water into a container and seal it. No gas can get in. Now you've got degassed water if you ever need it. Here's an example of solubility of solids relative to temperature and their solubility in water. And actually, if you look these values up in a reference manual like CRC handbook, you'll see them listed in these terms: grams of solute per 100 grams of water. Right. So that's percent. Right. Actually, it's not. It's percent mass, but it doesn't include the mass of the solute. So that's a different mass percent. Right? Don't get that confused with the first one that we discussed. So what you see is as temperature increases, solubility of sugar increases, potassium nitrate, sodium bromide, little potassium bromide, potassium chloride, those all increase with temperature. But sodium sulfate and cerium sulfate all decrease in solubility with temperature. And there are theories, but there's no good explanation yet as to why that happens. Here's the solubility of gases in water. Methane goes way down with temperature, oxygen. So you see a negative slope on all of these. Helium starts out low and stays low with temperature. So we used that fact to our advantage when we had aqueous solutions that we used for our high pressure liquid chromatography. When that solution goes into our chromatography tubes, right, it's under high pressure. Right? It comes out the other end, low pressure. So what happens when the pressure lets off? Any dissolved gas in that solution will go like that and play havoc with your detectors. And so we don't want any dissolved gas in our mobile phase. This is the mobile phase, and then you got packing in here for the chromatography. That's the stationary phase. So how do we get the gas out of this mobile phase? Well, there's several things you can do. Right? One is you can heat it. Right? Heat it up, drive it out, and then seal it so it doesn't absorb gas anymore. That takes a little too much time. So what we used to do is bubble, like those aquarium centered things, whatever you call them, centered rocks. Bubble helium through them into our mobile phase. And that would displace all the other gases. And helium has a very, very low solubility. So when it comes out over here, it's not a problem. Its solubility doesn't change that much with temperature or under pressure. That's called sparging. The other thing you can do, and a lot of modern high pressure liquid chromatographs now use countercurrent exchange with a vacuum. So you have your mobile phase is in here like this, and there's a membrane here. So your mobile phase is moving this direction, and you got a vacuum being pulled on this side. Right? And that vacuum draws the gases out through the membrane and let your mobile phase keep going before you start putting it under high pressure. All right. So here's an illustration of how we know that that the process is an equilibrium process between the vaporization of the solvent and its condensation. Notice on the left in that bell jar, we have pure water. Right? So it's vaporizing at a very high vapor pressure. But on the right-hand side, we have an aqueous solution of something. Something that works really good is a fairly concentrated sulfuric acid. So what's happening is, as you increase the concentration of the solute, the vapor pressure of the liquid goes down. Because two things. At the surface of the liquid, and you have a liquid in here, and you got solute molecules, and they're also at the surface. They are obstructing the vaporization of your solvent molecules. Plus, there's usually an attraction. If there's a solution there, that means there's attraction between the solute and the solvent. So they're holding back the solvent molecules from going in the solution. So the vapor pressure there is lower. All right, so what's happening is the water is vaporizing faster from the pure side than it is from the concentrated side. And they're each trying to establish equilibrium. But the one that is absorbing more water molecules into it is the one with the solution. And eventually, all the water molecules migrate from the pure water over into the solution. I've seen that happen. It's pretty weird. Nevertheless, true. So we can determine the vapor pressures of solutions. Only got 10 minutes. Vapor pressures of solutions using the mole fraction concentration. If we know the vapor pressure of pure solvent, and we also know what is the mole fraction of that solvent in our solution. This has to be the mole fraction of the solvent. Then that product will give us the vapor pressure of the solution. It's that simple. Now, this is Rayleigh's law. And this form of Rayleigh's law requires that the solute be non-volatile. So something like sodium chloride would be a good example, or sugar. They're non-volatile. This works. Normally, though, solutions are given in terms of mole fraction of the solute. So, like I showed you earlier, if you know the solute mole fraction, subtract it from 1, and you get the solvent mole fraction. That's what's required here. Now, that's for a non-volatile solute. But there are many examples where the solute and the solvent are both volatile. So we need a modified Rayleigh's law. Modified. Okay. In order to modify that rule, what we need is both the vapor pressure of the pure solvent and the vapor pressure of the pure solute. And then we also need to know the mole fraction of the solute. So this will give the actual vapor pressure of the solution. See, I got that on the next slide. Here we go. There it is. Okay. In this case, we're just saying component A and component B. We're not even making a distinction between which is the solvent and which is the solute. But what we do notice is that the ideal situation is on the left. If we graph these, okay, and we say this one references the mole fraction of either component A or component B. In this way, the mole fraction of A is increasing toward that side. So if it starts off at 0 here and ends up at mole fraction 1 here, this would be A. Okay. Mole fraction, if mole fraction of A is 1, that means no more solution. And then the other component, B, is increasing in this direction, right? It's decreasing that way, but it's increasing this way. And that way, this references A, and this references B. So if we're starting at 0 with B here, and we go, let's say, higher, go here, right? So as B increases toward 1, its mole fraction does that. And this is the vapor pressure of each component. Right? So the vapor pressure increases here as you get more B, and it increases here as you get more A. Well, the total vapor pressure is the combination of the two. So if we pick any point on this graph, we can go from here and then add this much to it. Add that much to it would be up here somewhere. It's about that distance. There. If we do that for every point on that graph, we get a line here between this one and that one. This is the vapor pressure of the solution under ideal circumstances. Okay. Now, as luck would have it, all solutions are not ideal. They deviate. So the deviation that we notice is for either strong solvent-solute interactions. Now, we're not saying that the solution never forms. We're saying that when it forms, what are the interactions? So if there's a strong solute interaction, then that interaction would actually decrease the vapor pressure of A in this case, and decrease the vapor pressure of B in this case. Why? Because if they're interacting, they're not letting their neighbors exit the surface and contribute to the vapor pressure. So they're decreased. When you add those together now, you get a deviation that's negative. This is a negative deviation, and it's due to strong solvent-solute interaction. Okay? Now, if you have weak solute-solvent interaction or even repulsive, then you get deviation going the other direction. It's going to go high. I'll use dotted lines. It's going to increase and encourage the neighbors to exit the surface into vapor phase. And that converts this one now to a positive deviation. All right. So, examples. If you have no interaction whatsoever between the two, you should expect an ideal behavior, right? A straight line, straight line, straight line. An example for that one would be, well, if the delta H of the solution is virtually zero, then you know that there's very little interaction. Benzene and toluene fit that bill. Benzene is like this. Right? Toluene has a similar structure, except it has a methyl group out here. So there's not that much difference between the two. How about acetone and water? Acetone and water have very strong attraction for one another. Right? So they would produce a negative deviation. And when you put acetone in water, you should expect an exothermic reaction. They have a very strong attraction for one another compared to their pure environment. And then acetone in water then would show a negative deviation. This. A positive deviation would be something like ethanol and hexane. They are soluble in one another. They just don't like one another very well. There's a repulsion there. And what you find is that you have an endothermic process. It takes a little heat, takes a little energy to get them together. Once you do, you find out that it absorbs energy from the environment. They're endothermic. And what that means is that they don't like one another a whole lot. When they finally get back together in delta H3, so ethanol and hexane produce a positive deviation. They repel one another, and they contribute to each other's vapor pressure. All right, I'm gonna skip that. We don't have enough time. Colligative properties. We got just a few minutes. So what I'm hoping is we can finish the review next week And you will have, you will have looked at the method for our lab. And I can talk about it for just a few minutes and clear up any misconceptions. The one colligative property that we're going to focus on for the lab next week is freezing point depression. Okay. What is a colligative property? A colligative property is one that changes for different concentrations of the solute, but it doesn't matter what the solute is. A higher concentration will change the value, but you don't have to know what the solute is. So we're going to use that to our advantage. Remember when we were doing empirical formulas versus molecular formulas? Right. We could get the empirical formula from the percent composition of the compound. That was easy. But then we needed to know what is the true molar mass of the compound in order to go to the molecular formula. Well, this is any one of these four, depending on which compound it is, can be used to determine the molar mass of the compound. You don't have to know what the compound is. Boiling point elevation, freezing point depression. What that means is a change in temperature. Boiling point changes in temperature depending upon the concentration of the solute. Freezing point is depressed as the concentration of the solute increases. Osmotic pressure, I'll have to define what that is, and vapor pressure we've already talked about. So let's go to the boiling point elevation. This formula, boiling point elevation, I need a new marker. Yeah. Boiling point elevation can be expressed as a change in temperature. And actually, absolute value is best, because all we want to know is how much did it change. We know that the boiling point is going to increase as we add solute. Right? So that's why you can boil water, you can make water hotter at its boiling point if you add a bunch of salt to it. So your spaghetti or your macaroni probably cooks at a higher temperature than just boiling water, because we generally add some salt to it. Now, it won't change it much. You have to add a lot of salt to be a major change, but it does change. That change is dependent upon a constant, the boiling point proportionality constant for water. Now, this value does change depending on the solvent. So this will be a value for our water. This will be a different value for lauric acid, which next week is going to be our solvent. And that's in the method, actually. And then we need to know the molality of the solute. This is why we needed an expression in terms of mass of the solvent and not volume, because we're looking at a change in temperature. Okay? Now, the freezing point depression is the one we're going to use. Freezing point depression is similarly like this. So I emphasized early on last year or last semester, you get a delta value by final minus initial. Right? And that's still true. But in this case, we don't care about the sign. We know in this expression, the freezing point's going to be depressed. But the only way the formula works is if we throw out the negative. So we got another value here for the freezing point of the solvent. And then we have the molarity, the molality of the solute. Okay? Come on. There we go. Now, I don't have time to explain this, and it's not going to be pivotal to your passing the course. So just study it if you want. This is an attempt in explaining using a phase a temperature pressure diagram like we looked at before for carbon dioxide and water, what shift takes place in the solution that would explain the change in boiling point, the change in freezing point. All right, I'm going to save this till next. We're going to have to talk about this in terms of your wait. Okay. I'm sorry, we don't have enough time to discuss that. I will mention this, the Van Hoff factor. This references any compound that dissociates when it goes into solution. So the Van Hoff factor for glucose, which does not dissociate in solution, I equals 1. Right. If you have to go ahead. I'm just going to keep recording. For sodium chloride, right, when it goes into aqueous solution, it breaks into 2 parts. So now I is equal to 2. You have to make that adjustment. This is if the molality is in terms of the molecular formula. I should say the formula unit. If you have something that breaks into 3 parts, then I is equal to 3. Right? And there are other examples. This is to compensate for this dissociation. Now, when in dilute solutions, this I value is very nearly how many ions per molecule are produced. Right? So 3 here would be I is 3, 2, there's 1 there. When the concentrations get very, very high, then we can have a phenomenon called ion pairing. And that usually only occurs with high concentrations and very small ions. So in that case, instead of 2 for every 1, you get maybe 1.8 for every 1 because some of them repair in solution. All right. Let's see. Simply because with increased concentration and smaller size, you get a stronger attraction for them. And there are more of them close together. So there's our modified equation. All right, I'm going to skip this. And I'll just leave it up there long enough for it to be recorded. We'll see you next week.
What puzzle are they doing next week?
Exam. Week after. Yep, week after. You can do them as soon as you want. That's fine.
For this, what do you write?
For now, that's it. But for the first experiment, this week I'm gonna cut you guys some slack on the first experiment. What you do is you write the name of the experiment and the page it starts on. So you would go over here to I'll just move over to some convenient place and only write on the right hand side title and then the other information that I mentioned that you need. Right. That we did talk about that. Okay.
For the lab?
Yeah, for the lab. And I gave you handouts. Yeah, I did give you good. So you got those to go by. What I expect to see before you actually go into the lab. Yeah. Okay. So I'm just flipping through these slowly so that you can see the question and see how it's worked out. Primarily so that I can get to a discussion of the next colligative property, which is osmotic pressure. Osmosis. Osmosis is defined as the flow of the solvent through a membrane in response to a difference in concentration on either side of the membrane. So what we're saying is that this membrane is semi-permeable, and we're going to keep it simple. we're talking about solutions that have water as a solvent. The semi-permeable membrane in aqueous solution. So we have water molecules over here, water molecules over here. And if you only have water on both sides, there's no movement, right? There's no movement of water either direction that we perceive. Of course, like I've said before, at the microscopic level, they're always going this way and this way, but they're at equilibrium. All right. What happens if we introduce a solute, of course, that cannot pass through the membrane, like sodium chloride? So we have sodium ions here, chloride ions there. Well, what happens is you reduce the number of water molecules that actually see that membrane. So their rate of transit through the membrane decreases because they're being attracted to these ions, plus they're being obstructed from approaching the membrane. So which way does the water tend to move? Well, it moves this way until the rates of movement are equal. They go backwards and forwards. Well, what would increase the rate? What would increase the rate of water moving this way so that eventually we could balance them? It's pressure. If you let the water move this way until the pressure on this side increases to balance the pressure on that side, then you reach equilibrium. That difference in pressure that you are required to reach that equilibrium is the osmotic pressure. Now I'm going to show you the practical way to the experimental way to show osmotic pressure, and it'll make more sense. So this symbol is pi. It's the Greek pi, like pi r squared. It's represented, this is osmotic pressure in atmospheres. And the formula for it is molarity, gas constant, times temperature. Now, why can we use molarity here? Well, because this gas constant is 0.08206 liter atmospheres per mole K. Right? So that temperature has to be in K. Oh, okay. Right? So this is going to, if this has to be in Kelvin. Yes. So this cancels the temperature, right? It's not effect because of that. This is atmospheres here. This is liters per mole times moles per liter, cancels that out. So that leaves us with osmotic pressure. All right. Here's an example, an expression of what you would see. On the inside of that bulb is a concentrated solution of some non-volatile solute. And on the outside is the pure solvent, or in this case, we might say water. And remember which way that the solvent is going to move. It's going to move into and toward the concentrated solution until the solution rises high enough to exert enough pressure to where the rates of passage through the membrane are now equal. We've reached equilibrium. This is another way to express it. And what you see is the pure solvent on this side and the solution on this side. So we're going to get movement of the solvent through the membrane until the difference in these two levels is the osmotic pressure, and the equilibrium is established at that point. Now, the Van Hoff correction is also important for osmotic pressure because it depends upon the molarity of the solute. And if you have a solute that dissociates in solution, then you need that correction factor. Okay? So this is an example where we would calculate the molar mass of a compound based upon its osmotic pressure. I'm not sure if I've got this worked out in detail. I hope I do. Yeah. So with those factors, right, here's the osmotic pressure, here's the temperature of the water. This gives us the mass of the compound, and this relative to the milliliters gives us the concentration. But we don't know the molarity. We can't tell that because we don't know the compound yet. So what we need is the osmotic pressure on the left in atmospheres, 588 divided by 760, right? There's the molarity as our unknown right there. There's our constant. I've left out the units of measure for compactness. And this is the temperature in Kelvin. So what we find is that the molarity of the solution is 3.16 times 10 to the minus 2 molar. Then we use that value in our next slide because molarity times volume equals moles. Remember that? Molarity equals moles per unit volume. And if we want to know the moles of the solution, N equals M times V. We just determine the molarity, the molarity at 3.16 times 10 to the minus 2 molar. And we also have the volume of the solution, which is 0.01 liters. It was 10 milliliters, 0.01 liters. That gives us 3.164 times 10 to the minus 4 moles. Now that we have the moles and we have milligrams, which is 0.0334 grams, we have enough information to calculate the molar mass. Grams divided by moles is molar mass, and the molar mass is 106. All right. I put this slide together to illustrate the natural phenomenon of using osmotic pressure to accomplish a physiological process. In this case, we're talking about sequoias, you know, the big California trees. How does the water get to the top of a sequoia? Right? If it's 300 feet tall and you can only get water to go up a tube 33 feet at 1 atmosphere external pressure if you pull a vacuum on it. That's it. That's as far as it'll move. So you can't get water to the top of a sequoia by vacuum at the top alone. You can't pull it up that way or push it up with atmospheric pressure. Now, at one time, we thought that possibly there was a surface tension factor, right? As the leaves have stomates in them, right? These cells on either side can swell and close off at night so the tree doesn't desiccate while it doesn't need to expel water. And then during the day, it opens up and then gas exchange can happen. Then water vapor can be lost there. Well, if you look at a microscopic scale, if you've got water here, let's see, at the stomate, you've got water. And what happens is, as water evaporates, it increases the volume, right? And surface tension doesn't like that. So it pulls back down, right? It pulls back down flat. And that causes a tension on the water. It pulls the water toward it. And it was theorized that maybe with thousands and millions of those stomates doing the same thing, that it could pull water to the top of the tree. Well, various experiments were performed and found that wasn't enough. That didn't do it. I don't remember the details, but it just didn't work. So then what we discovered was that there's an osmotic pressure difference between water in the soil and sap in the roots. Moving across that membrane, what's the osmotic pressure built up in the root as a consequence of the difference in concentration within the sap and the concentrations of solutes in the solution outside the roots. And it was measured, actually, with microprobes. It was measured at 20 atmospheres for these trees. 20 atmospheres of osmotic pressure in those rootlets. All right. The question is 20 atmospheres enough? Will it drive water to, by pushing water through osmotic pressure, will it push water to the top of that tree? All right. First of all, we need to know how tall the tree is in millimeters. Right? So that's the first conversion. 9.1 times 10 to the fourth millimeters is the how tall a 300-foot tree is. Then we need to know how tall is the water column that would exert 20 atmospheres of pressure. Right? So 20 atmospheres we convert to millimeters of mercury. Right? That's the first step. And then we convert millimeters of mercury to millimeters of water and compare them. Right? Millimeters of water, 20 atmospheres represented 2 times 10 to the 5th millimeter column. Whereas the tree is only 9 times 10 to the 4th millimeters tall. So we've got almost twice as much pressure as needed to drive water to the top of that tree. Yes, it will work. Osmosis and osmotic pressure will drive water to the top of a sequoia. Now, we're nearing the end. We're going to talk about a little bit about colloids. And this is the last topic. Up to this point, we've talked about solutions. And we know what a solution is, how to make a solution. We know theoretically what happens when a solution is formed. Right? We break the solute parts and we break the bonds for the solvent, make a hole, and then we put them together. And the solute fits into those holes. Well, for a colloid, we're talking about a suspension, not a solution. And a suspension is based primarily upon particle size. You know that the suspending medium, and we could make it anything, water for instance, has a certain amount of kinetic energy. The water molecules are moving at a given temperature, they're moving at a certain speed, right? This way, that way. And if you've got any suspension particles, suspended medium in there, then they're going to be impacted, right, by those suspending medium molecules, right? If there's enough energy and there's gravity always pulling them down, pulling these suspended particles, pulling them down, but if you've got enough energy, kinetic energy in the suspending medium to impact them, it will counteract the gravitational forces and not allow those suspended particles to drop out. At that point, you have a colloid. A colloid is not a solution, but it will not settle out also. Most suspensions, the particle sizes are large enough, they will settle, like sand in water, for instance. But a colloid, the particles are small enough, on the order of 1 to 1,000 nanometers. They're small enough so that they will remain suspended. These are different types of colloids, right? The dispersing medium on the left is analogous to the solvent, and the dispersed substance on the right here, right? Analogous to the solvent. This is analogous to the solute, the dispersed substance. So in the first one, we're dispersing a liquid in a gas. It's called an aerosol. Fog is a good example. The water droplet sizes are so small that they remain suspended. Smoke is a solid suspended in a gas. It's also considered an aerosol. A gas suspended in a liquid is a foam. A liquid suspended in another liquid, like milk or mayonnaise, is an emulsion, right? How do we get milk to remain unseparated, right? If you have a source of raw milk and you take it home with you, eventually it will separate into cream on top, okay? Or you can churn it and make butter. You can separate the oily parts from the water parts. Those parts, those globules of fat will not stay separated. They will not separate from the water. So processors that homogenize milk, your milk is homogenized. What they do is they take milk and they drive it under high pressure through a stainless steel sieve with very small pores in it. And those pores are so small that the fat globules, when they reach those pores, are broken up into small pieces. They only go through the holes if they're small enough. And if they're small enough now, they remain suspended in your milk indefinitely. Solids in liquids are like gelatin, Jello. Right? Jello is a protein suspended in water with sugar. Right? And that gelatin is derived from animal bones and hooves. They come from the slaughter, so we don't waste any parts. And the gelatin is a protein that is not very digestible in the human system. So when you eat Jello, unless it's got sugar in it, you get no nutritional value whatsoever. A gas suspended in a solid is a type of foam also. Like a gas suspended in a liquid is a foam, a gas suspended in a solid is a solid foam. A liquid suspended in a solid, like cheese or butter, is a solid emulsion. And we also have examples of solids in solids. Ruby glass is one of those. So what is one way that you can separate a colloid is to coagulate. And basically what happens is when you coagulate, you cause the small particles of the colloid, the suspended medium, to associate with one another. And they become so large that now the suspending medium can no longer support them, and they either drop out of solution or they float to the top, in the case of separating cream from milk. So the destruction of that colloid is not really destroying the molecule, it's destroying the colloid, the suspension effect. And it can be accomplished by several methods. The most common is heat it or add some electrolyte like salt, sodium chloride, or some other salt. And many colloids are of scientific interest are proteins. So it's or nucleic acids, and it's very easy to separate those from their suspended phase by simply either heating them and denaturing the molecule or salting it out. That's it. We're done for chapter 11. Next week, we'll do a review of chapter 10 and 11 in preparation for exam the following week. And hopefully we'll have a little time after the review so that we can talk about the method that we're going to do in the lab next week, which is the freezing point molar mass by freezing point depression. So prepare that lab in your notebook. You all know how to do that already. And we're done for today.